Okay, and you're live, Rich.
All right. Well, good morning, everyone. Good morning to those in Australia, and good afternoon for those of us in the United States. My name is Rich Ambrose. I'm a professor in environmental health sciences at UCLA. And today's symposium is sponsored by the UC Irvine Water-PIRE, which is a project funded by the National Science Foundation. And it supports research with our Australian colleagues on the use of low-impact development, or as they say in Australia, water-sensitive urban design for water supply augmentation and ecosystem restoration. So as part of the outreach for the UCI Water-PIRE, we're hosting a series of mini symposiums on different aspects of LID research and practice. So the first of these focused on the use of LID for reducing flood risk in urban areas. The second one was on incentives and barriers to LID adoption. The third one was on the use of LID for water supply and augmentation. And today's mini symposium will focus on green infrastructure and the environment. So we're fortunate to have a really excellent group of speakers today, really the leading researchers in the area. And I'll start by introducing everybody, and if everyone can just wave when I introduce you, then we'll move on from there. So in the order of talks, we first have Professor Tim Fletcher, who's Professor of Urban Eco-Hydrology at the University of Melbourne.
Hello there.
We have me going next. I'm a professor in the Department of Environmental Health Sciences, as I said. Next we have Professor Stan Grant from UCI, Professor in Civil and Environmental Engineering, and he's our fearless leader who's the director of the UCI Water-PIRE. We have Perran Cook, who's Associate Professor in the School of Chemistry at Monash University. And then we will finish with Dr. Megan Rippy, who's a PIRE postdoc at UC Irvine. So the symposium format will be each speaker gives a short 15-minute talk, and then we'll have some time for short questions and answers after each speaker. And then after everybody's finished their presentations, we'll have a roundtable discussion. And then we'll conclude the symposium. Oh, and I guess I should also introduce two people who are participating but not going to be speaking. That's Brandon Winfrey, who, up there he is, waving, and Andrew Mehring, who, and both of those are postdocs, Brandon at UCLA and Andrew at Scripps Institution of Oceanography. Okay, so without further ado, let's introduce our first speaker, Professor Tim Fletcher, who's going to be speaking on lessons from Little Stringy Bark Creek.
All right, thank you very much, Richard. It's really great to be here and talking to you. So this is the third of these seminars I've been involved in, and I've been really impressed by the kind of the range of things presented and I suppose the commonality between what's happening in Australia and what's happening in the US. So I just realised that I've actually the first slide on my presentation has got the incorrect title, but I'll correct that verbally. So on the title slide here, so Little Stringy Bark Creek project. So that title says Linking Urban Flooding and Stream Ecology, which is not the title I was intending, but I think it points to a really important synergy that we're exploring in this project, which is to try to see if we can benefit the receiving water environment in terms of ecosystem health at the same time as delivering a number of other important ecosystem services, including flood mitigation and water supply. I spoke about water supply yesterday, so I encourage you all to go and have a look at that one when it's online as a module. So I'll talk a little bit about those synergies as we go through. You'll see from this slide that there is a very big list of co-authors, and I particularly want to pay tribute to Chris Walsh. Quite a few of you will know that name. He's I suppose a well-known researcher in urban stream ecology, one of the authors of the Urban Stream Syndrome paper, which is an often cited paper, and he's really the spiritual leader, in my view, of this project. All right, so on to the next slide, which is entitled Urban Stormwater Runoff Degrades Streams. So I suppose it's a very obvious point, but really the point we're trying to make here is that when we go to a stream like we see on the right-hand side there and see that it's degraded, the instinct is to try to get into the stream and do things to fix it. And yet, what's driving that degradation in most cases is the traditional approach to stormwater management, which is to pipe all impervious runoff into the stream. And if we go to the next slide, this is really the foundation of the hypothesis underpinning this project, and that is that if we want to restore the health of these streams, and when I use the term restore, I'm not using it in a binary sense of that restoration is only delivering the stream to its natural pristine state. I'm talking about improving its health. It's according to a range of ecological metrics, so it may not get back to its original state, but certainly to improve its condition. So we hypothesize that achieving that is only going to be possible by essentially mitigating that stormwater impact, and that means reducing the size and frequency of untreated runoff, restoring the quality and pattern of filtered flows, so that's the next point on the build, reducing the volume of runoff to match the pre-developed volume. So in other words, trying to engineer into an urban catchment the same sort of water balance and hydrologic processes as would have happened in a forest. So it doesn't mean bringing the forest back, that's not possible, but it does mean trying to engineer those same water balances and fluxes into the landscape. So our test catchment is the Little Stringy Creek catchment in the east of Melbourne, Mount Evelyn, 4.5 square kilometre catchment. If you click on the next slide, which is titled Study Sites and Monitoring, so a really important part of this experiment is that it's part of a BACRI design, so before, after, control, reference, impact. And this is a really important element of robust designs for an experiment of this type. That is, if we intervene in this catchment, putting in place a whole range of stormwater control measures, and see changes in the catchment, we can only really be confident that it's our works that have caused these changes if we monitor control catchments, so other urban catchments where we're not intervening, and reference catchments, so forested catchments, to see that they're not changing at the same rate, because it could be climate that's causing change. On to the next slide. So Little Stringy Creek catchment, as I say, 4.5 square kilometres, about 13% total imperviousness. If your slides have got builds in them, then click to the next build. It's made up of typical residential kind of areas, so ranging from sort of 400 square metre allotments to much larger. We've got some commercial areas and also some industrial areas. So clicking through those couple of builds, you'll see there's an area with some factories, etc. Okay, on to the next slide. So 300 stormwater retention systems constructed over 2009 to 2015. So our intervention in this catchment has seen us construct systems from the allotment scale, so in individual households, through to the very large scale, so some very large stormwater harvesting systems providing water for regional sports facilities, and in between where we have, for example, constructed some large rain gardens or bioretention systems, and some quite significant harvesting systems supplying, for example, the car washing at a gas station. On to the next slide, which is a plot showing the connected impervious area over time from pretty much the start of our project through till 2015, when most of our work's finished. We're still doing some. But you'll see we were sitting at around a connected impervious area of around 10% of the catchment, and we're now down to somewhere around 5.5%. We're sitting at around 5.5% now. On to the next slide, hypothesized mechanisms and responses, which again for you may have several builds, so I'll step you through those. So we hypothesized that by reducing the connected impervious areas on the next build, we're going to reduce the size and frequency of polluted storm flows going into the stream. We're going to increase the amount of base flow, so restore some of that base flow by restoring infiltration. Combined, these will reduce the concentrations of a range of pollutants and the loads. This will also reduce the transport of some coarse sediments, so keep those coarse sediments which are important for habitat in the stream. This will subsequently reduce algal growth and we'll start to get a greater diversity of species in the streams. We will reduce microbial leaf breakdown and a range of other kind of indicators. And importantly, in the final build on this slide, we will increase the retention and the transformation of pollutants. So we'll give that channel back some of its capacity to retain and transform nutrients, particularly nitrogen. And for those of you interested in that area, I'd recommend reading the work of people like Peter Groffman. All right, so if you click on the next slide, which is monitoring at different scales. So whilst we've been implementing all of these works, some 300 odd systems, and it's actually been our team that's kind of led the implementation of those, we've been monitoring, and we monitor at a range of scales, which is quite important, because an important research question is if we manage, for example, to change the stormwater behaviour at the site by infiltration and rainwater tank, etc. A question is, how far does that benefit propagate downstream? And so we are monitoring at the site scale, then in the precinct, so perhaps a whole street area with maybe 20 houses, then through to the tributaries, and then through to the whole stream, so that we can start to see how that propagation proceeds. On to the next slide. So just to have a look at, we're just going to look at a couple of things, water quality and hydrology. So we've been doing continuous rainfall and stream flow monitoring. So this is next slide, data questions. And then water quality sampling since 2001. And so our question is obviously, have the hydrology, the water quality and the ecology, when we won't talk too much about the ecology today, changed as a result of our intervention in ways that we don't see in the reference and control catchments. So on to the next slide. So this is two plots of runoff coefficient, so the amount of runoff produced for a given rainfall event. And I note, as is apparent on the slides, that these are preliminary data. What you see is, following our intervention, which started very slowly in kind of 2009, but really took off sort of late 2013, I suppose. A lot of the big works were done there. We see a fairly significant reduction in the runoff coefficient. And if we compare that with Brushy Creek below, one of our control catchments, we also see a little bit of a reduction in runoff coefficient, in part because of rainfall changes. But if we use techniques such as change point analysis, we see that for Little Stringy Bark Creek we have a highly significant change, and for our control and reference catchments any changes are not significant. So that gives us some sense that we've done things in Little Stringy Bark Creek that are having an impact. One of our PhD students, Sung-Ying Lee, so she's been looking at fitting models to these changes, and sure enough she finds the same thing, that the Little Stringy Bark Creek catchment shows a very distinct decrease in runoff coefficient after accounting for seasonality and rainfall, and we do not see that significant trend over time in our other catchments. On to the next slide, which is called significant decline in runoff coefficient. So just making the point in another way, we see this quite significant change in Little Stringy Bark Creek that's not apparent in other catchments. All right, on to the next slide, which is water quality. So this is really quite significant. And I'll just take a little bit of time to step you through this. So the very messy looking plots that look like they came off one of those computer trace printers of the early 1980s. That is the raw data, and the green is our reference catchments. So these are our forested catchments. The purple are our control catchments. So these are urban catchments we're not intervening in. And the orange is Little Stringy Bark Creek. So what you see is that subsequent to our major works, we see a very significant decline in total phosphorus concentration, and we see the same for the soluble fraction of phosphorus, we see the same for nitrogen, and we see the same for sediments. That is a very significant change point, and interestingly, having been very typical of a urban stream anywhere around Melbourne or anywhere around Sydney or any other city in Australia, a Little Stringy Bark Creek now sits at a level that is consistent with our local state environment protection policy for upland rural stream, or pretty much on the edge of the requirement for a forested stream. So we've seen a really quite a substantial change in the water quality of this stream, which gives us, I suppose, great confidence that we're on the right track. Before I go to the conclusions, I'll just make the point that our ecological monitoring, so we're doing lots of ecological monitoring, and I don't present it here because it's early days, but so far we haven't seen significant ecological responses. We have, so we think that poses interesting questions. Is it simply because there's a lag, or is it because there are other factors that need to be overcome? And for example, the changes in the substrate and habitat complexity that have resulted from previous erosion. So that's a topic of our current research. On to the conclusion slide. So early signs of, early but quite clear signs of improvement to hydrology and water quality. So we're quite optimistic and quite excited to be able to show this. Ecological responses not yet shown, and this is really where our research interest now lies. We are just finishing some work, so we're working with Melbourne Water to do the last works in the next few months, and we're really hoping to be able to communicate the results of this over the next year or two as we bring the intervention stage of the project to its completion. Thank you very much.
Okay, thanks very much, Tim. And I'll open it now for questions if anybody has any questions.
I have one. Hey, thanks, Tim. That was great. I was wondering, about the other ecological indicators, and the fact that you haven't seen quite as much of a change. So can you hear me okay?
Yeah, sure.
Okay. Yeah, that you haven't seen quite as much of a change there yet. And I was wondering, in the case of aquatic invertebrates and things, I mean, a lot of those things are probably recolonizing from downstream. And your improvements are covering a massive area, but I mean, if there's degradation below, where a lot of the improvements have been done, do you think it's possible that you won't have a source population to recolonize from?
I'm wondering whether you've been sneakily reading our research grant applications. Yeah, this is exactly the question that we want to ask, and we have designed some experiments to test exactly that question. I think that that question of recolonisation, distances and sources is really, really interesting. Interestingly, in this catchment, actually downstream is in better condition because it's flowing sort of away from Melbourne at that point. And we actually do see some sources of colonisers downstream, and we, from what we've seen so far, we see them kind of getting closer to us, coming towards us. So the theory that build it and they will come might be true, but it looks like perhaps it's build it and they will slowly come. Anyway, we'll see. It's definitely, you've hit exactly on the question that we're interested in.
Great, thanks.
I have a question, Tim, as well. I was wondering sort of at what point you would start thinking about moving away from sort of the catchment scale interventions and into sort of in-stream interventions, and what those early ones might look like. Yeah,
that's a really nice question. This is exactly, you've hit exactly on the kind of sequencing we see. We've actually discouraged Melbourne Water from doing any in-channel interventions now, not because we don't think it's a good idea, but because we want to separate out the effect. And our intention is to do exactly as you say, and I've been arguing with my colleague Chris Walsh about whether he can put off his retirement to see this done. At the moment he's saying no, but our intention would be to, for example, monitor this over the next 4 or 5 years as it is, and then start some quite intensive interventions. And those would be things such as restoring some habitat diversity, so woody debris, etc. Perhaps replacing some of the coarse debris that's been, coarse sediment that's been lost. So actually replenishing that supply of coarse sediment, and then starting to deal with the incised sections of the channel. And I think that that will really be an interesting, completion of the work. And in yesterday's seminar, I made the point that our motivation for this project is not really to save one stream. Our big picture motivation is that if we show that it's possible, it forms an argument for protecting the streams that are not yet degraded. So those areas that are still going to get urbanisation, to do that urbanisation in a way that doesn't degrade the stream. And so I think the question you ask really is a really important one, because we have to kind of go all the way to completion to show this is how, in a new area where you've got quite a healthy stream, this is how you should manage the catchment, and this is what you should do in terms of the channel itself.
So I have a follow-up on that, because Little Stringy Bark Creek is in relatively good shape in terms of how much impervious surface you have compared to much more urbanized watersheds. And I wonder if you could just talk about what might be possible in a much more urbanized watershed. I mean, you're working towards pretty close to a full restoration in that watershed. Probably not possible when it's much more urbanized, but what do you think is possible?
Yeah, so perhaps I'll start with the last part. So we probably won't get to where we'd want to be in terms of bringing the impervious area down to a level where we would think there'd be no impacts. Constraints are going to stop us doing that, and so that's also going to be an interesting question. Is it still good enough? What's quite depressing about the stream ecosystem response to urbanisation is how non-linear and brutal it is. How rapid the decline is for very low levels of imperviousness. So there's a nice bit of work led by Ryan King in the northwest US that shows, they studied about 1,000 catchments, and they showed by the time you get to about 2% impervious area, you've lost a very high proportion of your taxa, and we see the same in Australia. So your question is a good one. What about catchments where we're 30–40% impervious? Should we just say, oh, let's not even bother? Or so two answers to that question. The first is that the benefits of a project like this are not just about restoration of the stream. They're also about supplying water, quite a significant water resource, which I talked about yesterday. They're about mitigating flooding. They're about improving kind of urban amenities. So you could even argue if you didn't care about streams, you might do it anyway. That's the first thing. The second thing is, as I say, our big picture motivation is to provide guidelines for how you protect streams, or where you might want to get to. Now, if I think of a catchment that's 30% impervious, I know, or 40% or 50, I know I'm not going to get there in 10 years. But if I say to myself, well, let's put in place planning controls so that every time a new building is built, or one is renovated, or a new bit of road is resurfaced, etc., and remembering that in Melbourne, for example, the turnover rate is about 2% per year. So in other words, on average, in 50 years, every surface has been replaced. Bit of a simplification, but close enough. That means that over a few decades, we might actually hope to get some of these quite degraded streams back to a state where we could restore them. Now, I find when I say that, a lot of people say, oh, that's 50 years, we can't really be planning for that. But my view would be, well, if that's our attitude to environmental problems, then I reckon we've got zero chance of dealing with something like climate change, because we're not going to make significant impacts on global temperatures in the next 10 years. We're talking about kind of 100-year commitment to action. And as I said yesterday, my motivation for things like this is thinking about my little granddaughter and thinking about, what sort of world are we going to leave her, or am I going to leave her? And I want to leave her a world where the streams that we have today are in a better state than they are now, and they have a chance of being restored, rather than, just being allowed to kind of go further down the path of degradation. So yeah, I reckon it's a longer term view, but at the same time capitalizing on the other ecosystem services we deliver through these things anyway.
Yeah, that sounds good. Yeah, I think that's a good perspective, especially realizing there's many other benefits. It's easy to think about just the organisms, especially if you're an ecologist like me, to focus on that and not think about the other advantages.
Yeah, indeed.
Any other questions for Tim?
Maybe just real quickly, Tim, so you laid out a flow chart toward the beginning of your presentation in which you articulated a series of hypotheses regarding what might happen as you get the hydrological flow back to more of a pre-urban state, or at least reduce effective imperviousness. And I'm wondering, do you have in place teams to look at each of those hypotheses as you collect data? Like, for example, one of the boxes that struck me was the retention of coarse material, which is more, I guess, stream morphology, geomorphology. So is that a master plan for all of the papers you're going to be writing on this project?
Yeah, that's a really good point. So actually those series of hypotheses pretty much maps directly to the structure of our team. So that's right, we have little sub-teams, I suppose, dedicated to each of those, and that geomorphic work is led by Jeff Veets, who is doing a lot of that work, and we've got two new PhD students, Kathy Russell and Desmond Afosu, who are looking at exactly this question and mapping coarse sediment. For those of us who are geomorphically ignorant, and I put myself and Chris Walsh in that category, we are very excited because Melbourne Water had to remove an asbestos pipe high up in the catchment, and they did that, and they made, of course, a little bit of mess in the channel and liberated a bit of coarse sediment. And we've been quite surprised how long it's taking that to move through the channel. And with potentially unscientific eyes, we are attributing that to our reductions in peak flows. but we need the discipline and objectivity of Jeff to assess that, and so he's helping do that. But yeah, we're quite excited to see how slowly that that sort of pulse is moving through the stream, and so we've really got a lot more coarse sediment sitting there than we used to see stuff really migrate very quickly. So, yep, as I say, the structure of our team is built around those hypotheses, essentially.
Thank you.
Anybody else? All right, well, thanks very much, Tim. That was a really great talk. And I guess we'll move on to the next speaker, an excellent speaker. I'll be speaking myself about the urban stream syndrome. So I guess I'll give you a moment to pull up the PowerPoint. If we go then past the cover slide to slide 2, when we talk about urban stream syndrome, Tim also mentioned Chris Walsh is one of the earlier researchers who identified this really about 10 years ago. People started recognizing this, and it refers to a set of conditions related to the ecological degradation of streams in urban watersheds, and it's called a syndrome because there are many different attributes to it. So we're talking about changes in hydrology, stream geomorphology, pollutant loads, and stream ecology. So I'll do a brief overview of these different types of changes and talk about some of the studies that have been done, and then I'll finish with just talking a little bit about some of the solutions to this problem. So if we go to the next slide, slide 3, there's a Google Earth image here of a relatively undeveloped watershed in Orange County here by Laguna Beach. And so to illustrate what the urban stream syndrome represents, imagine in this undeveloped watershed that you're a raindrop and you're falling on the middle of this slide here in the image, and that raindrop's going to hit vegetation, so some of it will attach to the vegetation, some of it will be broken up as it hits the ground, some of it will hit the ground directly, some of that will be absorbed. Eventually, if there's enough rain, it runs off a little bit and slowly builds up into some runoff that goes into the streams that are illustrated here. If we go to the next slide, what happens, this is not one of the low urbanization watersheds. This also is in Orange County and Costa Mesa, but this is a very high impervious surface. So what happens to most of the raindrops that are falling on this sort of landscape is that they're hitting most likely impervious surface, a rooftop or concrete, and they quickly run off into this network of storm drains that we've developed, and they accumulate very quickly. And so if we go to the next slide, on the effects of urbanization, there's a lot of effects, as I mentioned before, on the urban stream syndrome, but largely what we're interested in is what happens on the hydrology. And so what this illustrates here, if you go from the top left where it's not urbanized, it's natural ground cover, you see that a lot of the water actually evaporates or is transpired from the plants. Some of it infiltrates, and a relatively small amount is runoff. And as we move down to greater and greater urbanization, we have the next diagram over to the right shows 10 to 20% impervious surface. We're starting to get more runoff, and then down in the lower right we have 75 to 100% impervious surface. We still get evapotranspiration, not as much transpiration because there aren't so many plants, but we get a very high amount of runoff. So what this does is it changes the hydrograph so it's much flashier. And the other thing that's not so clear from these diagrams or from my sort of thought exercise of being a raindrop is that we get more dry weather flow also, so that urban water use runs off the landscape all year round, and particularly in places like Southern California where we have naturally a very long season without much rainfall. our streams are changed so that not so much that we have reduced base flow, but we actually have increased base flow during the dry weather. If we go to the next slide, this just illustrates the hydrograph and what the effects of urbanization are. So if we start at the top graph, we see the bars are the rainfall, and the line is the discharge in the stream. And so you see shortly after the rainfall, there's an increase in the discharge. It peaks. You know, there's a lag time, but it peaks and then it drops away. And that's in a natural setting, natural landscape. After urbanization, on the bottom panel, you see that it's a much shorter lag time because the rain moves much more quickly into the streams, and it's also a much higher peak because much more gets into the stream rather than being absorbed or infiltrated, and then it drops off quickly too. So that's what we talk about when we're talking about a flashy hydrograph. So if we go to the next slide, so one of the consequences of that changes in hydrology, that's a very important consequence, is that we have changes on the stream geomorphology. This is a picture here from a stream in Orange County, Lower Oso Creek, and what we see here is, you know, greatly increased erosion from the stream, an enlargement of the channels, so they're wider channels, incised channels. In this case, the incision is about 20 feet or so, and as a result of that incision, the stream is disconnected from the floodplain. So, I mean, that has a continued hydrologic consequence, but it also has really important ecological consequences because that connection between the stream and the floodplain is really critical for many organisms and for a lot of the functions the ecological functions that streams perform. So if you go to the next slide, slide 8 here, we have effects of urbanization on pollutant levels. And this is just a quick illustration from NRC report, but it just shows 3 different types of pollutants, TSS, so total suspended solids, total phosphorus, and zinc. And it has the levels of those pollutants in different sorts of land uses, and I've highlighted in green here the open space. And so in each of these cases, the pollutant level is lower in the open space than it is once the landscape gets urbanized. And then finally, the next slide, I want to talk about effects of urbanization on stream ecology. So the stream organisms are pretty interesting because since they're living in the stream, they're really tightly dependent on those physical and chemical conditions in the water. So we find that the organisms are keyed into the amount of water flow, various aspects of habitat quality, but in particular sedimentation can have a very big effect on the suitability of the habitat for different organisms, and then of course the water chemistry. And so what we find is with urbanization we get changes to the organisms in response to those physical and chemical changes. We also, one of the consequences is get reductions in the number of native species in the stream, and then we also find increases in exotic species or invasive species in the stream. So in a few slides I'll give you some examples of these. In the next slide I just have one quick example. There's lots of examples of the changes in water chemistry, in particular in toxicity and effects on stream organisms. I just wanted to talk about this one study which was published just this year looking at the impacts of highway runoff on coho salmon. And so what this study did, the graphs show in 3 different years the rainfall, and then after a storm these researchers collected the runoff and they put adult salmon either in the highway runoff or clean well water. And what they were looking for is either mortality or what they call pre-spawn mortality syndrome. So that could be it could be death, but it also could be lethargy, loss of orientation, or loss of equilibrium. And the results are really quite striking. You can see in the little legend there's a jumping salmon that's asymptomatic, or a jumping salmon with an X through it, which is symptomatic or dead. And then for each of these collections, each bar, they're showing how many individual fish they had in each treatment, either the unexposed controls or the stormwater exposed treatment. And in every single case, when the fish were exposed to stormwater, they died or they had the symptoms of pre-spawn mortality syndrome. And in every case, when they were exposed to just the clean well water, they were asymptomatic. So this is a pretty dramatic example of the sorts of toxicity that can come when stormwater enters into the streams. I'm not going to talk about this, but this study is also especially interesting because after what the experiments that I show here, they passed the runoff through biofilters, and they found that it completely removed the toxicity to the salmon, and they became asymptomatic after the stormwater went through biofilters. But that's not my point today. Okay, so if we talk about the next slide, one of the critical things about the urban stream syndrome is that not only do we see these effects that I talked about, but especially these biological effects are occurring at very low levels of urbanization. I would say surprisingly low levels. I think if you think about the amount of development in a watershed that represents 2% or 10% of impervious area, it's not a lot of development, but what we find is that we are seeing these thresholds in effects at those sorts of urbanization levels. So it's different in different watersheds and in different populations. There are different sorts of thresholds, but they're often in the 10 to 15% range for fish, and in vertebrates they're even more sensitive, so it can be at as low as 1 or 2% of impervious surface cover. And the graph just gives an illustration of this from some work that was done in Washington, and you can see the stippled bars are where the habitat was in excellent condition, and the hatched bars are in degraded condition. There's a pretty quick switch from excellent to degraded right around 10% or so. So if we go to the next slide, what I want to talk about now is just some examples of what we've seen here in Southern California. And this first example is about stream communities in the Santa Monica Mountains. And the researchers were really focusing mainly on amphibians. And on the left side here, we've got a set of native amphibians. We've got a salamander and a tree frog and a toad. And then on the right side, we have introduced species, so introduced crayfish, bullfrog, and mosquito fish. So if we go to the next slide, we see that typical for the urban stream syndrome, we see changes to the physical habitat. I thought it might be interesting to look at sort of what those changes look like. On the right, there's just a sketch, a diagram of what a natural stream would look like with the 3 different habitat types that we generally recognize in streams, so riffles, pools, and runs. And so what you see on the left is that there's a lot of riffles, there are quite a few pools in these streams, and then there are some sections of runs. When we look on the right at what the habitat distribution looks like in urban streams, what we see is fewer pools and many fewer riffles and a lot of runs. So the run would be just a smooth section where the water is flowing relatively quickly, and so what it means is that there's a lot less habitat diversity in the urbanized streams, and there's also a higher water flow and increased water depth. And then, as I mentioned before, we've also found that the streams become much more permanent. So that's illustrated in the table below, which just talks about or shows the length of dry stream in urban versus natural. And so you can see that there's much less dry stream in the urban areas than there are in the natural areas. So next slide. So that has consequences on the species. So there's many different ways that we can look at this, but in streams, when we're interested in stream health, we often look at the invertebrate taxa, and there are some groups that are known to be sensitive to pollution and other sorts of disturbances. And probably the most popular group to look at are these EPT taxa, Ephemeroptera, Plecoptera, and Trichoptera. And so what this graph shows is a plot of the percent of all the invertebrates that were sensitive EPT species plotted against the amount of urbanization in the watershed. And what we see is at the lower levels of urbanization, we get high percentages of all the inverts are these sensitive species. But as soon as we get to about 8% urbanization, those EPT taxa drop out. And so this is another example of the threshold where we start seeing the urban stream syndrome. In this case, it's about 8% for these species. And if we go to the next slide, there's also, along with that, not only do we lose some of the native species, but we pick up introduced species. And so in this is just a listing of the streams that were studied in this Riley et al. Study, and above the line are the natural streams and below the line are the urban streams. And then in the columns are different species. On the left it's the native species, and on the right introduced species. And so what we see is there are some species, this Hyloregilla, the HYRE species, that's a very cosmopolitan species. They occur in all the streams. But there are other native species, this other tree frog and the California newt, which are basically only occurring in the natural streams. And conversely, we look at these introduced species, the crayfish and the bullfrog and exotic fishes, and we see that they almost exclusively occur in the urban streams. And so the physical and chemical changes that happen as a consequence of urbanization are both bad for native species, but it also turns out that they're good for the introduced species. And those introduced species can have a big effect on the ecosystem health, the way that the ecosystem functions. Okay, so if we go to the next slide, I have one other example here, this time from Australia. I wanted to have some global diversity in here, and this is from a study that was done around Sydney. And again, this study looked at macroinvertebrates as an indication of the health of the streams, the stream ecosystems. And what the plot shows here is the number of different sites of 3 different habitats. They looked at edge habitats, riffle habitats, and pools, so some of the same habitats I showed in the earlier slide. And you can see they had a lot of reference sites where there was less than 2% imperviousness, and then they had a number of sites that went from between 2 to 10% all the way up to 45% impervious, and those were their urban sites. And in this case, they're using 2% as that threshold for connected imperviousness. So if we go to the next slide, we see the results of this. And again, these are invertebrates that they're looking at. There's a number of different aspects of the invertebrate community that they're looking at. They're looking at total richness. The signal per habitat, signal is just a bioassessment index that they have calculated. And then on the bottom graph is our old friend, the EPT richness per habitat. And what you see in each case is that the urban streams consistently have lower whatever that index is that's showing the health or reflecting the health of the stream. So either lower richness, lower signal values, or lower EPT richness per habitat. And in addition, one of the things that they found here was that there was a lot more variation in the natural streams that were naturally vegetated than there was in the urban waterways. And so I think that reflects the homogenization of the habitat that we see when we get urbanization, and that's part of what brings in the introduced species, the exotic species. Okay, so that's a quick summary of some of the symptoms of the urban stream syndrome, and so what I want to do is just spend a very short time talking about possible solutions. The first one, and this is sort of the obvious way to think about if you've got a problem in the stream, especially if it's something like stream geomorphology where you've had either the incision or a disconnection from the floodplain. It seems like the most obvious solution might be to do an in-stream restoration, and we can restore stream geomorphology. We can increase the heterogeneity in stream habitats. We can make a stream that's in size be connected to a floodplain again. So these are all things that are, can be engineered and are possible, but they're really not the solution, at least not a sustainable solution to this urban stream syndrome, because it just doesn't address the root problem that's causing the decline in the stream ecology and in those physical and chemical conditions. So if we go to the next slide, we have sustainable solutions. So, these solutions fall under lots of different labels. We've got low impact development or water-wise urban design, green infrastructure, green streets, all those sorts of categories. But all of them have in common this idea that we need to disconnect stormwater runoff from the storm drains. We need to minimize the effect of imperviousness, and that's really the way to have a sustainable solution to this. So there's many different approaches. We've heard about some of those already, and we'll hear more in the future, but those would include things like stormwater detention basins, or we could use permeable pavement, or stormwater biofilters like rain gardens and bioswales. And then Tim just talked about the Little Stringy Bark Creek project, and this is, ultimately is really the direction that we should be aiming for. That would be our aspiration, I think, where you can actually restore a watershed by a network of biofilters or other LID techniques that could reduce the excess water flow and pollutants to the streams and allow the stream fauna and flora to recover. And that's most likely to be successful in watersheds that have relatively low impervious surface cover now, but even in urban watersheds there can be a benefit, as we just talked about. It can be, we may not be able to get it back to natural hydrology, we may not be able to get all of the species back either, but we can improve the stream conditions, and there's also these other co-benefits in terms of reducing pollutant loads to receiving waters, but also other sorts of ecosystem services that both in terms of sort of biological services, but also cultural, aesthetic services that that could be a benefit of these sorts of watershed restorations. And not very many attempts to restore entire watersheds so far, but we're definitely moving in that direction. And so, in conclusion, there's a lot of aspects to the urban stream syndrome, but it's really driven by changes in hydrology due to urbanization and especially the increase of impervious surfaces. And there are very extensive effects on stream ecology, reductions in native biodiversity or increases in introduced species. The effects are seen at a relatively low degree of urbanization, 2 to 15%, and they can be pretty dramatic effects even at that low amount of urbanization. And then finally, the sustainable solution has to be based on restoring hydrologic function. And that's it. So, any questions?
Yeah.
Yeah, hi, Perran.
Hi. Yeah, it was a great talk. Thanks. Is there any demonstration projects or push for projects like Stringy Bark Creek?
Yeah, so a little bit, and I think we're moving we're definitely moving in that direction, but I still think Little Stringy Bark Creek is sort of a global model. And if you think about how much work it's been to accomplish that, I guess you can get a feeling for why it's not done in more places. That's why I think what Tim was saying about using it as a model, I think that's really true. I think as people recognize that it is feasible, then it's possible that they will be inspired by that. Now, having said that, there are definitely efforts to do something like that in Los Angeles and in other places. But for us, it's driven by regulations that ultimately are trying to protect the ecology, but in the proximate, they're trying to reduce pollutant loads to receiving waters. And so we have under the Clean Water Act, we've got regulations that that dischargers have to pay attention to. And that's been going on for a long time, but more recently the dischargers have been viewed as being cities that have impervious surface, and so they're not actually, it's not a pipe, but it's viewed as a discharge. And so here in the Los Angeles area, for example, right now, all the watersheds, all the municipalities have formed into groups that have been producing enhanced watershed management plans, and those plans include a network of LID techniques. So it's much more urbanized than Little Stringy Bark Creek, and so it's not going to restore the watershed really, but it's going to really provide this network that it's driven not so much just because people want to do it, but because they're required by the law to do it.
Yeah, thanks.
Oh, we can't hear you, Stan.
Great talk and great introduction to the talk that I'm going to do as well.
Right.
I guess one thing I was going to clarify is this issue of what happens to base flow during urbanization. And I think that the answer is that it's very location specific. So of course in Southern California, as you rightly pointed out, we've actually experienced enormous increases in base flow with urbanization. There was a paper that came out in Geophysical Research Letters that looked at historical stream flow, for example, in the Los Angeles River. I think that the number was 500% increase over the last 100 years, something like that. So enormous increase in base flow. But I guess what I have come to understand from working with my colleagues in Australia is that we're fairly unusual, and we're unusual in the sense that we import so much water. So that increase in base flow is actually a symptom of massive interbasin water transfers.
Right.
Then in watersheds which do not have interbasin water transfers, more typically the pattern is with increasing urbanization, the base flow actually declines.
Yeah.
So I didn't realize this until I started interacting with all of my colleagues, because I thought this was the norm, but in fact I guess we may be a bit of an outlier because of all of the water we import.
Yeah, I think that's exactly right, yeah.
I did have a question too. I really loved your examples, and I thought the habitat shift, the decrease in diversity of riffle pool habitat was particularly interesting. And I wanted to know, I haven't read that paper, I definitely want to read it. The increase in the runs, is that concrete lining? Or is that a sort of a earthen stream which is just becoming less, less diverse in habitat?
Right. So there definitely are some concrete lined streams in this area, and that obviously just destroys the habitat heterogeneity. There's nothing, right? But that's not the case in those streams. Those streams are still natural bottom streams. It's just that presumably it's the hydrology, but it could be excess sedimentation. Something has reduced the heterogeneity in the streams, so that even though I know a lot of those streams because that's in my area, and so even if you know what stream they're talking about, you would not necessarily think that this was an impacted stream. You would not think that it was channelized or anything like that, because it's not. So it's actually a consequence of the urbanization. But if you went to the stream, unless you measured those things, you would not know that it had been altered that way, just to look at it. So another type of alteration that I didn't talk about at all, but now that you're talking about, sort of Southern California specific things, is changes in vegetation. And so in our streams, we don't worry so much about changes in vegetation. We definitely have riparian trees that are a part of the stream community, but they're not, people aren't as concerned about the loss of those trees. But if you go up to the Pacific Northwest or even Northern California, where we have salmonids, then the temperature increase is a huge impact on the salmon. And so in some places, that are one of the consequences of urbanization is actually having the removal of the trees. And then again, the stream could look exactly the same. And in fact, in that case, even if the habitats look the same, the habitat diversity, it's that change in the physical characteristic, the temperature, that completely destroys the quality of the stream for the salmonids.
Thank you.
Mm-hmm. All right, any other questions? Okay, well, let's go to our next speaker, Stan Grant, who's going to talk about restoring catchment hydrology.
Thank you, Rich. And like I said, I think that your talk is a great segue, as is Tim's actually, to what I wanted to chat about, which is really about, I think we all recognize that LID are a potential solution to the hydrological drivers of the urban stream syndrome. We've heard that over and over again. But if you drill down, at a watershed scale, what would be the right mix of the different types of LID that one might implement if you wanted to protect stream health, and also, what volumes of water should be specifically harvested and infiltrated. So I wanted to share with you a paper that was actually published by it was first authored by one of my graduate students, Asal Askarizadeh, but it was kind of a hive mind paper in the sense that we brought together researchers across the PIRE and tried to address this question in a kind of holistic way. And so if you go to slide 3, that's entitled The Urban Stream Syndrome, I think we've all now seen this a number of times. Basically, as Rich pointed out, the urban stream syndrome is a syndrome. It's a collection of symptoms. And sadly, all of these pictures were taken from Orange County, where UC Irvine is located. So, so these are all images of this urban stream syndrome that are actually quite close to home. And basically, the paper that I'm going to be talking about appeared last year in Environmental Science and Technology, and so that's the title and set of authors if you want to learn more. So if you go to the next slide, that is entitled "Increased Imperviousness Alters Stream Hydrology in 2 Ways," and this really comes from Chris Walsh's fine work and colleagues at the University of Melbourne. And kind of gets to the heart of one of the main drivers of the urban stream syndrome. And basically the idea is that during wet weather, you have too much water being delivered through formal drainage systems to streams. And what I mean by formal drainage systems are essentially the meat and potatoes of civil engineering, right? We train our undergrads to design formal drainages, and then they go to work for flood control districts who are very good at trying to reduce the risk of flooding in urban settings. And that means building hydraulically efficient systems that move runoff from the urban landscape to receiving waters very, very quickly. And as we've heard, that has all sorts of unfortunate ecological consequences, which is something that, for the PIRE, we're trying to bring that dimension to engineering undergraduate studies. So if you go to the next click in the animation, so basically you have the flip problem, again in settings where you don't have a lot of interbasin transfers of water, so I guess so take LA off the table here, but during dry weather, because you put this imperviousness down on the landscape, basically that shuts down infiltration of water, rainwater, and infiltration of water into the subsurface is a major source of base flow in streams in most watersheds. And so if you cut that off, then basically you reduce the base flow. So you have this kind of schizophrenic problem where you've got too much flow during rain events, and you have too little base flow during dry weather events. Again, excluding interbasin transfer issues. And if you click to the next animation, basically these two changes in the hydrologic regime of streams are primary causes of the urban stream syndrome, the pictures of which we saw in that earlier slide. And one can start getting kind of nerdy about it. You know, I come from an engineering background, and so again, kind of building off of some of Chris Walsh's and Tim Fletcher's very nice studies looking at applying environmental flow concepts to the urban stream syndrome. We just sort of riff off that. So there's a series of animations I'm going to click through. The first one basically is titled Annual Catchment Water Balance Pre-Urban. And I'm going to just click to that box there. And so in a pre-urban state, you can sort of imagine in a very, very simplified way, right, that the watershed is like a bucket. And that bucket receives rainfall in the form of mean annual rainfall. That's what MAR is. So that's kind of the input of water to the bucket. Some of that mean annual rainfall or flow into the bucket is going back to the atmosphere as evapotranspiration, as we've heard. And then some of it is being infiltrated in the subsurface, and the key thing is that subsurface flow is, at least in part, supplying base flow in streams during dry weather periods. And so if you click on the next part of the animation, basically you can write out that, annual water budget. So we're talking about an annual water budget in a really simple way. You basically say that the mean annual rainfall equals the evapotranspiration, click on the next animation, plus the annual stream flow, that's that S sub, which is in this conceptualization fed by subsurface infiltration. And of course, if you're watching carefully and you're not asleep yet, you'll immediately point out that not all of the infiltration is going to go to the stream. Some of it might be lost to deep groundwater. But for the sake of this this model, the simplification is that essentially all the water that infiltrates eventually makes it to the stream. So what happens when we start urbanizing, but we don't have low impact development? So that's the next set of animations. Basically, what happens is that we reduce the subsurface area, so we don't have as much infiltration going to the stream through the groundwater route or interflow route. And instead, we've got this formal drainage, which is represented by the runoff arrow. And that formal drainage is now delivering a large volume of water during storms directly to the stream. And we're referring to that stream flow as S sub EI here. So basically what we've done is we've changed the balance of the mean annual rainfall between ET, stream flow from subsurface transport of water, and then we've added this new term, stream flow from effective imperviousness, or that connected imperviousness that we were talking about. And you might wonder, how can you calculate the stream flow from the groundwater route and from effective imperviousness? And basically you can use this very simple set of equations which rely on stream coefficients and the fraction of the watershed which is essentially covered with effective imperviousness, or that connected imperviousness. And then in the bottom equation, that the stream flow from effective imperviousness, we're relying on an impervious runoff coefficient. And the key thing to note here is the stream coefficient and the impervious runoff coefficient can be measured and have been measured. And we'll get back to that in a second. So that's enough math. Let's just look at this graphically. So if we just choose arbitrarily, not entirely arbitrarily, but we just choose a couple of example values for the stream coefficient and the effective imperviousness coefficient of 0.3 and 0.8, we get graphs like the one shown on the bottom here, where at an effective imperviousness of 0, that would be the unurbanized state. Essentially 30% of the mean annual rainfall, that is 0.3 fraction, is going to subsurface flow and supporting stream flow, base flow in the streams. while the other portion, the 70%, is going to evapotranspiration. So that's kind of the pre-urban state. And then as we increase effective imperviousness, and that's the horizontal axis there, so we're increasing the fraction of the urban landscape which is covered with connected imperviousness to streams, what's happening is that the subsurface flow is being reduced because we're laying down that impervious surface and infiltration is reduced. Evapotranspiration is reduced because we're taking forests and grasslands and replacing them with impervious surfaces. And all of that extra water is going to impervious runoff. And so you see this really dramatic shift in the distribution of mean annual rainfall with much more red region, which is that impervious runoff, which is so bad for streams. So how do we fix that? And so, you know, thinking about LID through the lens of trying to repair this particular problem, what would we want to do? In the next animation, I'm basically showing a replumbing of that bucket, right? So we have all of that runoff from the connected imperviousness, and what we want to do is we want to capture all of it, ideally, locally, and do one of two things with it. We infiltrate it to the extent that we need to enhance the subsurface flow to mimic pre-urban conditions. And then the rest of that runoff we so-called harvest. We essentially use it for purposes which keep it out of the stream. So that's kind of the basic concept. And then if you click on the next animation, that you're seeing the sort of water balance that goes with that concept. Mean annual rainfall basically consists of these two terms in parentheses. One really represents the pre-urban evapotranspiration, which is the evapotranspiration under urban conditions, plus all the harvested water that you pick up with LID. And then the second term represents the pre-urban annual stream flow, again through subsurface routes, which in the urban case basically becomes a combination of what is left to infiltrate plus the infiltrated LID that we implement in the watershed. So that's kind of the basic concept. And if you go to the next slide, we're showing that replumbing graphically. Again, the same scenario. We have a stream coefficient of 0.3 and an effective imperviousness coefficient of 0.8. And what you're seeing in this slide is that the combination of subsurface flow and infiltrated runoff always equal 0.3% as the effective imperviousness increases. So the base flow is then unchanged. And then that extra wedge, the kind of pinkish red fraction of MAR at the bottom of that graph is the harvested runoff. So that's the runoff that we have available to use for toilet flushing and other activities which keep the water at least directly going into the stream. So that's kind of the basic concept. If you go to the next slide, the question that I want to get to now is what is the best mix of distributed LID for a specific catchment? And of course the answer to that question would depend on what your end goal is. But if you go to the next slide, keep clicking, sorry. If you had as an end goal restoring pre-urban stream hydrology like they're trying to do at least partially in Little Stringy Bark Creek, then as indicated in this nice Walsh et al. Paper that I highly recommend that you guys have a look at, there's these basic principles, right? One is that you would try to capture all of that stormwater. So this is basically the same thing I just showed graphically, but in words. So you capture all of the stormwater locally. You don't let any of it flow directly to the stream through the formal drainage system. A portion of that captured stormwater you're going to infiltrate to again restore the shallow groundwater and base flow in the stream. So that's exactly what we were saying with the infiltrated LID. And then the rest you harvest, you keep it out of the stream. So I'm basically just saying the same thing I did mathematically, but now in words. And if you click to the next slide, I'm showing a picture of some examples of biofilters configured in either an infiltration mode, which I'm going to start with, or in a harvest mode in a moment. So in an infiltration mode, the idea is that you would take that, and you can click forward one slide, you would take road runoff or roof runoff, you'd run it through into the biofilter, which of course is a vertically oriented system. We're going to hear more about that, I think, toward the end of this session. So the water ponds at the top, that little inset over in the lower right, the water ponds on the top, and then slowly moves through filter media, interacts with plants, and hopefully is cleaned in the process. The real point here is that this particular biofilter is unlined. And so if you think about where that water goes, it really goes to two places. One, some of it is going to evapotranspire because you've got plants and evaporation going on. So some of it's going to go back in the atmosphere, which is a good thing. That's a form of harvesting. And then the rest of it is going to infiltrate. And so in this mode, you've got some of that flow coming into the biofilter that's essentially harvested back into the atmosphere, and then some of it which is infiltrated into shallow groundwater to support stream flow. So if you go to the next slide, you can also operate a biofilter in a harvesting framework by just simply lining it so that the water, as it filters through the system, does not then enter the local groundwater, but instead goes into a pipe, which then you could treat and pump back into your home for maybe toilet flushing and other activities. And again, in this case, what we're essentially doing with that extra water is, again, some of it's going to go up into evapotranspiration, it's harvesting. The rest of it's going to go back into the home and be used for various purposes. Again, we call that harvesting. Eventually, it goes to the sanitary sewer system, is treated, and hopefully disposed of in a ecologically safe and friendly way. So if we want to restore pre-urban hydrology, the next question is, how much of the stormwater runoff should be infiltrated versus harvested? I mean, you know, we know that we want to restore these pre-urban conditions, but what is the right mix of the two types of LID? And it turns out, because the stream coefficient depends on the stream coefficient of the natural environment depends on the number of trees you have, essentially the fraction of the land that's forested, as well as on the mean annual rainfall. The answer to that question really is that the ratio of infiltrated to harvested runoff depends on the fraction of pre-urban land and on MAR, that mean annual rainfall. And the next graph is kind of showing that pictorially. Let me kind of walk you through this. So the vertical axis is showing the pre-urban fraction of forest. So if you imagine Los Angeles before anybody got here, you know, depending on where you were in Southern California, you would probably be somewhere along that vertical axis. Pasadena, I was guessing, was about 20% forested, and so that's that C1 there. City 1 would be my guess at what Pasadena might have looked at like in Southern California. And it has a mean annual rainfall of around 480 millimeters. So that's the C1 point. So that's the vertical axis, and again, the horizontal axis is the mean annual rainfall for a given region. The color basically is the ratio of the volume which you should infiltrate relative to the volume you should harvest for LID, expressed as a percent. So 100% means that you would infiltrate and harvest exactly the same volumes to maintain pre-urban condition, pre-urban hydrology. And the key thing that I want to, well, I guess there's one more thing I want to say. You can kind of see a general gradient going from red, which is a low percentage in the upper left, to kind of a deep purple, which is a high percentage in the lower right. And this really has to do with that pre-urban fraction of forest, because trees are very good at evapotranspiring. So they're much more effective at moving water into the atmosphere than is a grassland. And so as you increase the fraction of forest, basically that means that under the pre-urban condition, there was less water infiltrating. More of it was going back into the atmosphere. And that's particularly the case as the annual rainfall becomes low. And so that's why in that upper left corner, we're predicting that you should have much less emphasis on infiltration and more emphasis on harvesting to sort of mimic that, what used to be a lot of evapotranspiration from trees. The main thing that I want to say, there's a couple main things, I guess. One is the dark black line over toward the right is the 100% line. So that's the case where basically the volume of runoff that you should infiltrate and harvest is exactly equal. And if you imagine this plot represents the world, right? Most of the world lies to the left of that black line, which means that in general we need to infiltrate much less than we need to harvest. And that's great news for, you know, water-starved areas like Southern California, where we could use that stormwater runoff for other purposes, basically potable substitution, like flushing toilets. The other thing I wanted to point out is that thin line that goes through Pasadena, C1, that's essentially corresponding to the 30% infiltration to harvest ratio. So in Pasadena, we would ideally have a combination of LID, again, that captured all the runoff, and that 30% of the runoff was infiltrated relative to harvested. The other thing that's kind of interesting is that line crosses through C2, which is a very, very different environment. That would be Baltimore, Maryland. So a much wetter region with a much higher pre-urban fraction of forest. So you can basically have the same infiltration to harvest ratio in very different regions of the world. So clicking forward, how might we choose low impact development technologies to achieve a given harvest infiltration ratio? The beautiful thing about this framework is that basically we're just looking at getting the right ratio of infiltration to harvesting, and that means that we can categorize all LID technologies on the basis of the percentage of runoff that they harvest, infiltrate, or leave as runoff. And how do we do that? Well, we thought about it a little while, we argued about it, and we came up with this ternary diagram, which I'm calling here the LID universe. And basically, the key thing about ternary diagrams, in case you haven't encountered them before, is that any point in that ternary diagram kind of conserves mass. In other words, the end members have to add to 100%. So that dot that I've got located on the ternary diagram is essentially corresponding to 50% overland runoff, 40% harvested runoff, and 10% infiltrated runoff. And again, those add up to 100% of the runoff. So the key thing is that we can begin to populate this ternary diagram with different kinds of LID technologies. So let's start on the next slide with a biofilter, which is essentially unlined. So it's going to infiltrate, and it's also going to harvest through evapotranspiration. Basically, that's going to be toward the lower left. And these regions that we're mapping out here are actually based on published performance data for different LID. So it kind of maps over to the left on line biofilters. Click forward, line biofilters actually span a very large region because you can get different degrees of infiltration and harvesting with these guys depending on how you configure them. So they're actually quite versatile. If we just plot that in the next animation, the 30% infiltration to harvest ratio, that just plots down the ternary diagram. So we would be looking then for either combinations or individual LID, which sort of give us overall, when integrated over the watershed, that 30% infiltration to harvest ratio if we were in Pasadena, for example. Clicking forward, we can add things like green roofs and rain tanks and wetlands, which are really just about primarily harvesting, although a lot of them also leave the runoff going to streams. On the other hand, we can talk about infiltration trenches, and permeable pavement with drains and no drains. These tend to plot to the left because they're more infiltrative. And then finally, we added dry biosoils. Here is that green polygon in the next slide. So the point that I'm trying to make is that you could sort of see a sequence of ideas here that could guide the development of LID in a particular urban watershed. First, you start with kind of what is the pre-urban hydrology you're trying to get to. Second, what is the ratio of infiltration to harvesting of runoff that would achieve that pre-urban hydrology that you're interested in? And then that kind of leads to this sort of ternary diagram framework where you can start looking at the combinations of different LIDs that would give you that particular ratio. So here are my conclusions. Imperviousness changes stream hydrology by increasing flow during storm and reducing base flow during dry weather, exception being Los Angeles, where we've imported so much water that we actually have more base flow in the summer than we used to. Next slide. Distributed LID can restore pre-urban hydrology provided that all of the stormwater is harvested and infiltrated with an infiltration to harvest ratio that depends on the mean annual rainfall of your location and the pre-urban forest cover corresponding to your particular area. And when we map that out, we find that for most regions of the world, including Southern California, much more water should be harvested than infiltrated, which is a really great thing for reducing urban water or increasing urban water security. So with that, I'm very happy to take questions, and thank you.
Okay, thanks very much, Stan. That was really interesting. So any questions for Stan?
Yeah. Can you hear me?
Go ahead, Perran. Yeah.
Thanks, Stan. It was a lovely talk as usual. You've got a very elegant reductionist approach. It's a good way of getting insight. But I'm going to be a scientist, and which we always try to muddle things up. Engineers try to make things clear. I think scientists try to muddle things up, and it's just based on my own anecdotal experience. So in areas like Clayton, which is aptly named, there's a lot of clay in the soil. So, you know, again, I'm not a hydrologist, but my feeling is it's going to be very hard to get infiltration into those areas. I presume that sort of obviously factors in as well into the, you know, A, into how much infiltration there was prior to settlement, and then B, obviously guidelines and practice need to take into account how possible it is to get infiltration to happen.
Yeah, absolutely. So if you were to look at that review article that I mentioned at the beginning, about a third of it would be the reductionist stuff that I talked about, and you know, yay, we can do this, and it's really interesting. And then the other 2/3 is, wow, it's very site-specific and very complicated and very path-dependent. And so you're absolutely correct. I mean, and there's so many exceptions to the rule that maybe there isn't a rule anymore. Because of the fact that, I mean, you know, just to list off a few, you know, the sort of presence of clay may limit infiltration. On the other hand, you know, there was a talk by Scott Taylor a couple of days ago on the earlier symposium. He was basically you know, caveating all of this with concerns about groundwater contamination and transferring pollutants in surface water into groundwater, which is extremely difficult to remediate. I know that Tim in Little Stringy Bar Creek was very concerned about essentially pushing contaminants that were already in the ground essentially into the stream and causing more damage through increasing base flow. You know, and there's a lot of interesting kind of unintended consequences having to do with redox chemistry. You know, in the area that I live in, the San Diego Creek watershed has a lot of selenium in it, and as that the subsurface water becomes oxygenated, it can mobilize the selenium into streams, and then it becomes, you know, a massive water quality issue. So yeah, absolutely. I think that really this is just a way of beginning to think about how you would go from individual unit scales to watershed scales, but then of course all of the details of individual watersheds are going to have to come into play.
Yeah, thanks.
Other questions? So I have a question about forests. So I should know what a forest is, but I'm not sure what a forest is in your, you know, arrangement there, because, I mean, we have shrubs, we have chaparral, so we have native vegetation, they're just not trees. And so I'm not sure how much difference it makes what the vegetation type is, and you know, does it have to be a tree?
Yeah, well, I can be very specific about what that forest refers to, the F, the fraction of forest. That basically comes from an article published in Water Resources Research back in 2001, which I think has probably about 1,000 or so citations now, in which they took all of the stream coefficients from around, and as many stream coefficients as they could collect from around the world, and they essentially developed a hydrological model, which ultimately led to a correlation between the stream coefficient and mean annual rainfall and fraction of forest as they defined it. So, so I think that it's a very, yeah, I think that unpacking that would be very interesting. It's probably beyond what I could do, but it would be interesting to look back at that data set and see if the kinds of systems that you're referring to are included in the database that was utilized in Zhang et al.
Yeah, it's kind of strange because it depends on the context. Because, you know, mostly when people say forest, they mean trees, and that certainly might be the case here. But like the Forest Service, I mean, they do forest restoration in our local chaparral. I mean, and when you talk about forest fires or the Forest Service, they would pay attention to that vegetation too. So I just don't really know.
Yeah, and I think that in that particular case, I have no idea, I should say, but I would imagine chaparral is acclimated to pretty dry climates, and so therefore the evapotranspiration would be pretty low.
It is, yeah, that's true.
Yeah, so we'd absolutely go contrary to the kind of, you know, global assessment that Zhang et al. Is talking about.
Yeah. Okay.
Is there time for one more quick question, or do you need to move on?
I think we should take it.
Okay. You know, I had a chance to comment on this earlier, so I feel bad for saying something now. But I noticed for the wetlands, it's all, you know, either 100%, and on your ternary diagram, it's 100% overland runoff or 100% harvest with no infiltration. Since some of these do discharge downstream or to other areas, I mean, is it true to say that there's no infiltration going on when a wetland is put in?
I think that this is on a unit-by-unit basis. So thinking about it from an engineering perspective, you know, it's like a unit operation. It's like a, you know, a specific engineered system that you're putting into the ground. And so if sort of the concept was, and I really like this process because it kind of enforced some discipline in thinking, right? If you put a wetland in, one of the things that's characteristic about the wetland is that there's water in it even during potentially dry weather periods, and that means that you're not, you know, it can be flowing horizontally, but it's not infiltrating. And you know, I'm sure that there are exceptions to that. It's not, you know, 100%, but as a general rule, you wouldn't want to have a lot of infiltration in the wetland because it would dry out.
Okay.
And in many of these engineered systems, they're actually lined.
Right.
Mega's giving me some you know, little assists. It's like lined. Yeah. So that's the other thing. I think from an engineering perspective, they would be lined.
Okay.
Okay, I think we should move on to the next speaker, which is Perran Cook, who's going to talk about nitrate cycling and denitrification.
All right. Thanks for the introduction. So I just realised that the title of my slide is not correct. But basically, I've used this picture here. This is a nice estuary from far eastern Victoria, and the reason I've used it is because it sort of typifies a lot of the coastal systems around here, which are quite sandy and shallow, and that has some implications, I think, for some of the traditional views of or the importance of nitrogen cycling. Sorry, just also before I proceed, I'd just like to acknowledge Ryan Woodland, my co-author. He's actually now in Maryland, so if some of this work piques your interest. He is a fellow American, and he's back over on your side of the world, and of course also Adam Kessler, who's was one of my grad students and is now doing a postdoc with me. So if we move to the next slide after the intro slide, I'm just going to quickly go over some of the things I'm going to talk about. I'm going to talk about, just introduce what nitrification and denitrification are. They're two key transformations in the nitrogen cycle. Then I'm going to go on to talk about some recent insights into denitrification in coastal waters, and some of it's our work and some of it's just from the literature. And then finally I'm going to just present a bit of a case study on the effect of nitrogen loading on estuarine systems in Victoria. And I think this is obviously very important. It's in the context of LID, which is obviously what the topic of this forum is. Okay, so just starting off on a conceptual model of the nitrogen cycle. So I'll just walk you through this diagram here. So we can conceive of a few important parts of this diagram. The first is the blue part is the water column, and then we've got the brown, which is the sediment. And I've subdivided that into two zones, which is delineated by the dashed line going horizontally across the page. We've got the oxic zone and then the anoxic zone of the sediment. The oxic zone is typically a few millimeters thick. And we can think of nitrogen, Org-N here, which is organic nitrogen, being broken down to ammonia. So the origin of that organic nitrogen is basically phytoplankton in the water column, detritus, being broken down. So the first step in the nitrogen cycle is actually the production of ammonium. And that occurs both in the oxic and the anoxic zone. If we then continue through the nitrogen cycle, so some of that ammonium that's produced in the sediment can be released to the water column, and the significance of that is that is bioavailable nitrogen. So that is basically nitrogen that can be taken up by phytoplankton. And so just to come to one of the key points of this talk is why are we even talking about nitrogen? And the reason that nitrogen is important is because it's one of the limiting nutrients in coastal ecosystems. Basically, it's the missing ingredient that you need to make algae grow. So particularly in Port Phillip Bay is a good example. You put in nitrogen and basically you pretty well instantaneously get algae growth within a few days. So most coastal ecosystems are very highly nitrogen limited. And as we put more nitrogen into those systems, we turn them greener and greener. And that can be both phytoplankton, so algae in the water column, and that can also be macroalgae, for example, sea lettuce, which you see around the coastal areas that have high nitrogen inputs. And I'll show you some pictures of that later. We also have the next step in the nitrogen cycle, which is the conversion of ammonium to nitrate, and that is called nitrification. And that, of course, only occurs in the oxic zone, right? So that needs oxygen to occur. So this is an essential link in the nitrogen cycle because nitrate is the precursor to denitrification. So some of that nitrate can be released to the water column, which is also bioavailable for phytoplankton, but particularly in deep, dark, muddy sediments, a large amount of that nitrate diffuses into the anoxic zone of the sediment, and at that point it is used as an alternative electron acceptor to oxygen by bacteria. So many bacteria are what we call facultative denitrifiers. They can basically denitrify when nitrate is available, and that produces N2 gas. And the reason that we're interested in this process is that it represents a sink for bioavailable nitrogen. So N2 gas is no longer bioavailable. In chemical terms, it's basically two nitrogen atoms bonded together with a very strong triple bond, which means that it's not really accessible to any organisms except for organisms that can fix nitrogen, which we call diazotrophs. And so that process is very energetically intensive. So primarily phytoplankton and algae get their nitrogen from the fixed forms, which are nitrate and ammonium, and this denitrification is a sink for nitrogen. So a big control over the rate of denitrification is the degree to this coupling of nitrification and denitrification, as we say. And so if we go on to another slide, I've sort of highlighted those key steps in the nitrogen cycle in this yellow box. So we've got organic nitrogen being degraded to ammonium, which is then nitrified to nitrate. That's an essential step. That nitrate then diffuses into the anoxic zone where it's lost as N2 gas. We can also define denitrification efficiency, and this is also a useful way of conceiving of how efficient the sediments are at removing nitrogen from the sediment. So percent denitrification efficiency is just defined as the flux of nitrogen divided by the total flux of inorganic nitrogen out of the sediment. So that's the flux of nitrate plus the flux of ammonium plus the flux of N2. So if we now then move on from that slide, which was the percent denitrification efficiency slide, I've now returned to that conceptual diagram that I showed before. And what happens, one of the key things that happens in ecosystems, particularly coastal areas, as organic matter loading increases, so we get more productivity, more phytoplankton reaching the sediment surface, that oxic layer becomes thinner as more oxygen is consumed. The upshot of that thinning of the oxic layer is that we have less nitrification, and then the final upshot of that is that we have less denitrification as well. So at a sort of first glance, it's somewhat paradoxical. Denitrification is an anaerobic process, and if we add more organic matter to make the system more anoxic, we actually decrease it, and of course the reason for that is that there's this essential oxic step in the middle that needs to occur. So if we now move on to the next slide, what I have is a plot of denitrification efficiency versus the DIC, or the CO2 flux from the sediment. And the reason it's plotted versus CO2 flux is that's basically a proxy for how much organic matter is entering the sediment. And the key point is that we move from a denitrification efficiency of around 70% down to very low denitrification efficiencies as more and more organic matter reaches the sediment, i.e. as the system becomes more eutrophic, more algal growth. So healthy coastal ecosystems we can conceive of typically having a denitrification of around 70%. I'd like to stress that this is based on studies in primarily muddy sediments. And I think also it's fair to say that many of these studies have also been undertaken in sediments which aren't euphotic, so there isn't light reaching the sediment surface. And so these two, whether or not something's a cohesive muddy sediment versus a sandy permeable sediment, and also depending on the productivity of the sediment, has important implications for how much denitrification actually can take place. So what I'm going to do now is just, if we now move on to the next slide, I just want to talk about a couple of case studies. The first is the role of microphytobenthos, benthic algae. So this is microscopic algae which lives on muddy sediments. Often you look at a muddy sediment, particularly in shallow waters, and you may think, well, there's nothing actually growing there. But in actual fact, if you take that sediment and stick it in some acetone or some ethanol, the acetone and ethanol go extremely green. So there's a huge amount of algae on those sediment surfaces, and that's referred to as microphytobenthos. I'm also going to talk about denitrification in permeable sediments, and that's something that's been a focus of my research over the last 10 years, picking that up from my postdoc, which I did at the Max Planck for marine microbiology in Germany, and Markus Hüttel is really the person that got permeable sediments on the map in terms of their importance in nutrient cycle or biogeochemical cycles in general. And I'm going to pose the question, or I'm going to be a bit. It often doesn't go down very well with my colleagues, but because denitrification is often, it's quite a popular process, and in a way I feel like I'm trying to talk it down a bit. I like denitrification. I'm not trying to talk it down, but I think all my studies show that maybe it's a bit less important than we think it is. So I'm being a bit provocative here. Okay, so one of the first studies is going back to the early 2000s, and of course the Danes do some marvelous biogeochemistry, and often their papers have some great insights. And so there was a debate over the 90s and even possibly to the present day as to the effect of benthic microalgae on denitrification. The early thought was that benthic algae would actually increase denitrification, and the reason for that was it was thought that, well, it's known obviously that algae, when they photosynthesize, they increase the thickness of the oxic zone in the sediment, which should lead to an increase in nitrification. But of course, against that potential stimulatory effect, we need to temper the assimilative demand for the algae themselves for nitrogen. So basically, they're creating competition for the nitrifying and the denitrifying bacteria. And I think, in general, it's fair to say that the algal assimilation of nitrogen really trumps any stimulatory effect from oxygen. And so what this graph here shows nicely, so moving on now, I'm not sure if I might have missed to signals progressing the slide. So I'm on the slide titled Algae Reduce Denitrification Through Competition for Nitrogen now. And what this plot quite clearly shows is that denitrification, and this is denoted here on the y-axis as Dn, that's denitrification which is driven by coupled denitrification. Okay, so it requires the nitrification step. So we see that in sediments colonized by algae, we have very low rates of Dn. Okay, so that's the leftmost bar. What they did then also in this experiment was also added nitrogen to the treatment with benthic algae, and we can see that there was a stimulation of denitrification, and particularly in the light. And so this supports the hypothesis that oxygen production from photosynthesis can stimulate nitrification and denitrification, but it needs to be replete with N for that to work. And then finally, the rightmost bar basically shows that sediments heterotrophic, grown in the absence of algae, and I think this is the low-end treatment, basically have the highest rates of denitrification. And so what we can clearly see there is that the competition for nitrogen between algae and bacteria, the algae win. So basically, key upshot there is that in euphotic sediments, we would expect to see relatively little denitrification compared to assimilation. Next slide. And what I've now thrown in here is some measurements of denitrification from local systems. So this is in Western Port, which is a very large intertidal bay to the southeast of Melbourne. And what I have here is two plots, just two study sites, which I think are fair to say show the general picture of the system, where we have the rate of denitrification or nitrogen fixation on the y-axis, and then we've got different conditions, whether it's dark. V is vegetated, dark non-vegetated. So vegetated is with seagrass, which is Zostera, primarily Zostera mulleri, and non-vegetated is basically where we've got Microphytobenthos. DN and DW are the two rates of denitrification. DN represents denitrification from coupled with nitrification. DW represents denitrification driven by nitrate from the water column. And the key thing is we can see that the rates are very low, okay, so they're almost non-existent, which again matches with the previous slide. So basically, denitrification doesn't really take place in sediments where there's a lot of light. And on the flip side of this, we actually see that the sediments are a net source of nitrogen, so there's a lot of nitrogen fixation. So I haven't introduced this process. Nitrogen fixation is the opposite of denitrification. It's effectively where N2 is taken from the atmosphere and converted into a bioavailable form like ammonium. And what was quite interesting about this is we see high rates of N fixation both on vegetated and unvegetated sediments. Vegetated sediments colonised by seagrass are known to have high rates of N fixation. That's well known. Less recognised in unvegetated sediments. And we think the key driver there is actually cyanobacteria, which are very abundant on these sediments. So key thing is that very limited euphotic sediments really hang on to their nitrogen tightly and even actually add more to the system. And I've also now, if we go to the next slide, just basically showed another slide, and this is some work from Emily. Now, unfortunately, Emily can't present today, and she may have had this slide in her presentation. I understand she is going to put it in the presentation, so I hope I'm not stealing any of her thunder. But the key thing here is, well, this is just one slide I've stolen from her paper, which basically looked at the fate of nitrate in a range of biofilters, and we can see we've got the green area there, which basically shows assimilation. We've got denitrification represented in the blue, and then we've got the yellow representing remaining nitrate in the biofilter. And the key take-home message for this, I don't want to spend too much time on it, is that in the presence of assimilative demand, so vegetation, denitrification seems to be the loser. So if you give a system with lots of plants nitrogen, they take it over denitrification. All right, moving on to the next slide. So now that sort of finished up what I wanted to say about the role of plants, I'm now going to move on to permeable sediments. So permeable sediments, basically sand sediments, they're quite different to cohesive sediments, and the key difference is, in the context of what I'm going to discuss, is that water can flow through them. So intuitively, I think we know that if you basically dig a hole at the beach and you get a bucket of water and you tip it into the hole, the water disappears pretty quickly, right? And that's quite clearly because the sand is permeable, the water moves through it. If you dug a hole in the mud and did the same thing, the water wouldn't disappear. So this has some very interesting implications for how elements are cycled in sandy sediments. I've animated this slide here, and I've now got some arrows there. I don't know if they've hopefully come up. So what I've got here is a side-on view of some sand, and this is in a flume that we've set up in the lab. So basically the current is flowing. I think it's flowing from the left to the right, it doesn't really matter. And what that current does flowing over that rippled surface is it leads to high pressure and low pressure areas. And we get high pressure areas in the ripple crests and low pressure areas at the, in the ripple troughs. So the low pressure area are the high pressure areas and the low pressure areas are over the ripple crests. So what that leads to is this water flowing through the sediment, as I've indicated by those arrows. And we can graphically see this effect if we look at just the colour of the sediment. The black there is indicative of reducing conditions, so conditions in the absence of oxygen, and the more yellow golden colour represents oxic conditions. So we can quite clearly see from this slide that oxygen is being pumped into the into the sediment. So one of the questions that I've been working on, particularly Adam's really progressed this over the last 4 years, is, well, how does nitrogen cycle in these permeable sediments compared to how they cycle in the cohesive sediments? I apologise, I've now moved on to the next slide, so now I'm on the schematic diagram of cohesive and permeable sediment. If we look on the left side of it, we've got the cohesive sediment, which basically represents the nitrogen cycle that I've already introduced. We have ammonium being produced in the deeper layers of sediment, diffused into the oxic layer. When nitrification occurs, the nitrate then diffuses back down into the anoxic zone where it's denitrified. In contrast, if we now look to the right side of the diagram, we can see that we have a situation which is changed by advection, as we call it, or movement of water through the sediment. We have a larger, thicker oxic zone, and we have where nitrogen can be oxidized to nitrate. The nitrate can then be pumped down into the anoxic zone, where it's then denitrified. Now, initially, when I started thinking about denitrification in permeable sediments, and this was way back in the day with Marcus in the early 2000s, we sort of thought that, yeah, permeable sediments are going to be a massive sink for nitrogen, and the reason is, of course, you've got this big fat oxic layer. You're going to have a huge amount of nitrification, and then the advection is going to pump all that nitrate into the anoxic zone, and it's all going to be denitrified. So, just thinking conceptually, we thought, yeah, this is going to be really exciting. We're going to see huge rates of denitrification in permeable sediments. Now, if we move on to the next slide, I've probably got this a bit out of order. I probably should have put this on the previously, but what this slide shows is basically an image of oxygen, side-on view of oxygen in these permeable sediments, and this can using a planar optode. So Ronnie Glood basically invented these, so we've been working quite a lot with him, and basically you can see 100% saturation of oxygen in the water column, and then these very distinct zones of oxygenation within the ripples where the water is pumped in, and then these anoxic black zones where the water is moving out of the ripple. And so what Adam did as part of his honours project, and also moving into his PhD, was he set up a model to describe the oxygen and nitrogen cycle in permeable sediments. Now, people have been doing this for decades in cohesive sediments because you only need a one-dimensional model, and they're relatively easy to set up. Again, it was through my work with in my postdoc where I saw this being done, these two-dimensional models being set up, and that was with Jack Middleburg. I need to acknowledge him here because he was one of the person who got the ball rolling using COMSOL to set up two-dimensional models to describe nitrogen cycling in permeable sediments. And so what Adam was able to do with this model is, if we look at the top diagram, we can see oxygen distribution throughout the sediment. And the model simulates very nicely that two-dimensional distribution around the ripple. And then if we look down below that, we can now see a model of denitrification in permeable sediment. So those hot spots you can see in the sediment indicate the regions where denitrification is taking place. Now, in muddy sediments, it's relatively easy to measure denitrification, and people have been doing that for the best part of 2 decades now, whereas in permeable sediments, it's actually really bloody hard to measure denitrification. We've been doing it in our flume, but part of the problem is when you've got a flume, you're always losing some of your labelled N2 gas to the atmosphere. So in practice, it's been really hard to measure denitrification in the flume, but what we can do is make measurements of the 15N2 concentrations in the pore water, and we can use that to validate our models. And so this is what Adam did quite successfully in his honours project, and also continued to do in his PhD. And I'll just quickly show one of the ways in which he validated that. And so one of those, again, was using the flume. And again, this was involving Ronnie as well, who really likes novel sensor techniques. And so we came up with this design. So now we've moved on to the next slide. So I've moved on from those images of oxygen distribution and nitrogen distribution in the sediment. I'm now on the slide where we've got the grey grids. So on the left we can see we have this grey grid, which is basically a sampler, and that grid had these little wells about 5 millimeters deep, and we filled each of those grid cells with an acrylamide gel. We then stuck that gel into the side of the flume, which is shown in schematic B, which basically gave us a cross-section of the ripples. What we then did is added tracer to the flume, and then we sampled those gel cells for 15N2, which we were able to use to put together a two-dimensional map of nitrogen, of 15N labeled nitrogen concentrations around the ripple. So now if we move on to the next slide, which has got those coloured figures, we've got on the left some measured distributions of 15N in the sediment, and on the right we've got some modelled distributions of 15N in the sediment. Now, the resolution isn't great, but it's as good as we could get within the detection limit of the method. So we could measure lots of, on the top diagram, we can measure this as total denitrification. So this is denitrification of the 15N tracer that we added. On the bottom diagram, we can also calculate the rate of coupled nitrification, so that's what we call DN, and we can see that the rates of that are very low. And the really significant part of this is that, again, if we put in the conditions that we had in the flume into the model, we can actually model both the spatial distribution and the concentrations, or the rates, with what I would regard as a pretty good match to what's being observed. So this gives us quite a degree of confidence that the model actually is giving us a realistic representation of what's going on in the sediment processes. And so, to cut a long story short, we basically then, if we now move on to the next slide, what we found with this model is that the rates of coupled denitrification within permeable sediments are extremely low. And again, this kind of, as you know, going back to our original hypothesis, this is very counterintuitive to what we expected. And I'll just talk you through this diagram now to sort of explain that. So if we now start at the top of the diagram, this is the scenario cohesive sediment. So in a muddy sediment, we have, as I've said, ammonium diffusing up from the anoxic zone into the oxic zone. The oxic zone of the sediment is only a few millimeters thick, so we have lots of nitrification occurring in that thin zone. We then have diffusion transporting that nitrate both up and down. Now, if we think about it, diffusion is actually a very fast process on the scale of millimeters. So quite a lot of the nitrate that is produced in that oxic zone is very rapidly diffused into the anoxic zone where denitrification takes place. And under optimum conditions, as we saw in the previous earlier slide, was that, not the previous, earlier slides, we'd get up to 70% denitrification occurring. If we now think about the scenario, moving down to the second part of the diagram to permeable sediments, the sort of scenario we have is as follows. We have these very stratified two-dimensional zones. So if we start down at the anoxic region of the sediment, we have ammonium being produced within the sediment. And the way that the water flows in permeable sediments is up through the ripple crests. So what that actually does is create a conduit for reduced nitrogen to be released directly into the water column. Nitrate, on the other hand, is typically cycled just through the oxic zone of the sediment. So there's actually very little crossover of the nitrate produced in the oxic zone into the anoxic zone. So this sort of gave us this conceptual diagram here where basically ammonia produced in the sediment is released to the water column, and the denitrification efficiencies we typically see in permeable sediments are down around 5, maximum maybe 5 to 10%. So the upshot of this was counter to what we thought. Denitrification in permeable sediments is extremely inefficient. Okay, so that's kind of finishes up just the little spiel I had on some of the process studies. I just want to now just finish up by just talking a little bit about some of our work where we've looked at the impacts of nitrogen loading on coastal systems. And the case study I'm going to use is the effect of nitrogen loading on estuarine vegetation across the state of Victoria. And what we undertook was a study where we selected a range of catchments ranging from pristine. So we're quite fortunate in Victoria. If we go to certain parts of the state, we still have catchments where the vegetation is effectively intact and there's been no development at all in the catchment, ranging through to extremely highly urbanised and also agriculturally dominated catchments. So now I'm on the slide focal point. Hopefully you've caught up to me. And so what we're looking at is the influence on nitrogen loading on the plant primary producer community. And so when I'm talking about primary producers, I'm talking about how the system shifts from seagrass to macroalgae. So now if we move on to the slide titled Primary Producers, the way we did this was using a combination of aerial imaging, so collaboration with engineering. One of the, actually the head of civil now has a plane, and so he took a whole lot of aerial images of estuaries across the state. And we also used boats to ground truth those aerial images to classify whether the sediment was bare, vegetated by macroalgae, or vegetated by seagrass. If we now move on to the second part of the slide, which has been animated, primary producers, what that diagram shows is, on the far left, shows a map of the one of the estuaries, the Curtis estuary, which is basically just some classification based on spot drops of an underwater camera that were made in the estuary. And then in the middle we can see some images of the different habitat types. So the top we can see macroalgae, so in this case we have ulva. In the middle we have an unvegetated sediment, so it's effectively microphytobenthos, and on the bottom we have a seagrass dominated sediment. So for the purpose of this study, the key thing that we're focusing on here is whether the ratio of seagrass to macroalgae. So if we now move on to the next slide, this is just an example of the sorts of vegetation maps that we produced. On the top and also on the bottom of the slide is a map of the different, or a map of Victoria showing the locations of the different estuaries. So and this was Ryan who undertook this work. He made these vegetation maps, and so what he did then was basically calculated the total area of the estuary that was either covered in seagrass versus macroalgae. So, and the way we then looked at this was as the ratio of macroalgae to total vegetation. So just moving on through the animation, we have a macroalgae to TV ratio of 0, representing pristine or clean seagrass. So this is the non-eutrophied state. Moving through to macroalgal to total vegetation ratios of 0.85 to 1, where we see the system is completely dominated by macroalgae, and we describe that as a quite eutrophied system. And so, as I said, we then looked at this ratio of macroalgae to total vegetation as a function of nitrogen loading. And so we now move on to the next slide, where we have this plot of macroalgae to total veg as a function. I apologise. The title of the x-axis has dropped off. The x-axis is DIN loading, so that's dissolved inorganic nitrogen, which is effectively nitrate loading. In tonnes per kilometres squared per year. So what we very clearly see is that as the nitrogen loading increases, we get this very rapid threshold at around 5 to 10 tonnes of nitrate per year, where we flip the system from being pretty well.
I can drive you.
Do you want to pick me up?
Sure. What time?
I don't know. It starts at 9.
Can someone mute, please? So we then see this very rapid change from low eutrophication, so dominated by seagrass, up to dominated by macroalgae at around, as I said, 5 tonnes per kilometre squared of the estuary per year. So I suppose the analogy here, listening to the other talks, is that we're seeing this very low and clear threshold. So the previous talks were talking about percent of the catchment that is impervious, but I think the threshold there was between 2 and 5% imperviousness. So we see very rapid flip at that point, and so here we're seeing quite a rapid flip from dominated by seagrass to dominated by algae, around 10 tonnes of nitrate per year. And the other interesting thing about this study, if we now move on to the next slide, is that the relationship is actually, so the relationship that we observed, which is shown here by the solid line, is remarkably similar to the relationship observed in other studies in the US. Now, these studies were undertaken not in the same way as us. We used a spatial gradient. Most of these were mostly undertaken by time series measures in the one estuary. So I think it's quite remarkable that we're seeing such a similar threshold, around 5, maybe 10 tonnes nitrogen per kilometre squared per year as the threshold for this change in benthic vegetation. Okay, so moving on now. What I've shown here is a slightly different plot, and probably I just want you to focus on the top right graph here. And I've again shown the same eutrophication index that we saw before on the y-axis, but instead of plotting it versus nitrogen load in this case, I've actually plotted it versus the percent of the catchment fertilised. Okay, so we're actually not even looking at any measures of nitrogen going into the system. All we're using is land information database to basically say, well, what percent of that catchment is fertilised? And we see quite clearly that relationship is extremely strong. So we don't even need to actually measure nitrogen loads. We can just look at the percent of the catchment fertilised to get an idea of the risk these estuaries have of being eutrophied. And I think this is very elegant because basically, you know, from a planning perspective, and also I think from an engineering perspective, we can simplify the problem down and allow us to sort of plan ways or working out ways to solve this problem from a much broader sort of landscape scale. All right, so I've got some text in there which is probably not all that relevant, so we'll just move on now. Okay, so if we now move on to the conclusion slide, I sort of think many shallow coastal systems there's very little nitrogen removal through denitrification. Nitrogen has a clear marked impact on coastal systems, as I showed, and that pattern of impact is, I think, very similar to what you observe throughout the world. So one of the questions I'm sort of posing in the context of this forum is I wonder whether the key focus of LID nitrogen removal should actually be in the agricultural areas, because I think, you know, these are the key culprits for nitrogen inputs, and particularly in the Australian context, it's seen as a really big growth industry in Australia. The Asian market is seen as being sort of a big growth area for our food, and one of the ways to increase our profits is to intensify our agriculture. And I guess the analogy there in the States is what's happened in the Mississippi Basin and the impacts of that on the Gulf of Mexico, creating that sort of dead zone of anoxia. So effectively the similar problem to what I just described, but on a much larger scale. And that's it from me. So thanks for listening.
Okay, thanks very much, Tim. So, Perran. So, do we have any questions for Perran?
I've got a bevy. Great talk. Really nice overview of a lot of the research that you're doing and some of the sort of key findings that you're excited about. I was really pleased to see that summarized so cleanly. I guess I had a couple of questions for you. One is this idea that that we're not getting much denitrification, if I understand correctly, because essentially the nitrate is really not able to mix into the anoxic zones very well. That in advectively dominated systems, basically you end up with this zonation that you talked about in the ES&T paper, which to some extent limits rates of denitrification. But then, you know, right now in the stream literature, there's a lot of interest in microzones, with the idea that heterogeneity within the sediment creates very localized regions of anoxia within bulk oxic regions, which actually end up dominating denitrification. And in fact, if you look at N2 evolution, you're seeing as much N2 evolution in oxic zones as in anoxic zones. So the time to go to anoxia isn't such a driver for denitrification in those circumstances. So I'm just wondering if the kind of different set of conclusions that you're coming to may speak to differences, fundamental differences in coastal permeable sediments versus stream permeable sediments, and specifically maybe less heterogeneity in the coastal sediments.
Thanks very much, Stan. That's a great point. And actually, I did mean to, I did have a note to self to sort of touch on that conundrum there. You know, we've obviously worked on some things where we've come to some different conclusions. So yes, fundamentally, there's a few key differences between streams which I think change the conclusion in stream sediments to what you're likely to see in coastal sediments. And the key one is that the nitrate concentration in stream sediments is many orders of magnitude higher than it is in coastal sediments. And I think the key part of the break in the nitrogen cycle is through the lack of nitrification. The zonation breaks nitrification. So coastal waters see very little nitrate. Streams have, as I said, massive amounts of nitrate. So the nitrification problem isn't there. So we have a lot of nitrate in the water being pumped into the sediment. And so then the question is how much of that actually makes it into anoxic zones. And again, as your very elegant analysis has shown, it's basically the path length and the dam collar number basically that determine whether it's going to end up going anoxic with nitrate present and being denitrified. So I think in streams, in the context of streams, that does occur more. So I think the degree of pumping of nitrate into the anoxic zone is much higher. And as you said too, I think this idea of heterogeneity. So you think of streams being full of CPOM, as they say, coarse particulate organic material. Terrestrial plants tend to be larger and lumpier than phytoplankton. So the idea of micro niches in coastal sediments, they talk about it. I'm yet to see much evidence of it. I did some experiments actually on this, where I dumped a pile of macroalgae into the flume. So we made these little anoxic, well, I wouldn't call them micro niches, I would call them sort of centimetre scale niches. And we were hoping to see lots of denitrification around those. And again, sort of what happened was in practice that the water was deflected around them, and there wasn't really a lot of entrainment of the nitrate into the anoxic zone. So in the context of coastal systems, I haven't seen much evidence for that. But I think the flow paths are probably a lot more complex in streams than they are in coastal waters. So I guess the upshot is I haven't given up on streams as being good denitrifiers as I have coastal waters.
So if I understand, then actually the limit is on the nitrification, as you see it, not so much getting the nitrate into the anoxic zone. And then yes. I was going to also ask, maybe it isn't as clear then about N2O production and incomplete denitrification, and so whether, ironically, the permeable sediments might be, great at producing a greenhouse gas. Yeah, look, I have done a few experiments looking for nitrous production, and I haven't seen a lot, but I've got to say I haven't done that exhaustively. I know that people are talking about that. I've heard some talk about that. I think the way I conceive of nitrous oxide production being, or the conditions under which I conceive of nitrous oxide production being high are, one, sort of we've got suboxic, so not completely anoxic, and secondly high nitrate. And so streams, I think, potentially could have a lot of nitrous oxide production. Yeah, and again, if it's sort of the mixing of the, so you have your anoxic chimney, and if it's a matter of kind of mixing the nitrate from an anoxic region into the anoxic chimney, that's kind of rate limiting, then maybe sort of partial denitrification would be an issue.
Yep.
So.
Yep.
And I don't mean to dominate. I just had one last question, and we have been looking at these planetary boundary issues, and a great paper in Science by Stefan et al. Looking at planetary boundaries and
yep.
basically fingering nitrate as being one together with phosphate, which is phosphorus, which is already crossed. And I asked one of my students to dig into that a little bit, and the answer was that it has to do with the possibility of a global ocean anoxia event, which geologically speaking happens. I'm just wondering if you can kind of comment on kind of where we are in overall nitrate release to the ocean, and how far away are we from a global ocean anoxic event if the planetary boundary has been crossed?
I think my feeling is we're quite a long way away. I think, depends on your context, right? I mean, Australia has relatively low, we see local effects, but I think there'd be nothing getting off the shelf, right? Because our systems are so starved, they just take everything up. So in the context of global, global relevance, the Mississippi, you need that sort of scale system. And in the Gulf of Mexico, you see it on a small scale.
Mm-hmm.
The Gulf of Mexico is probably, in my view, a worst case scenario because, apart from when you get hurricanes, I think it's fair to say that it's quite sheltered. It's quite, it's quite a calm ocean, and it's a relatively small sea given the volume of water coming down the Mississippi. So, to be honest, I think we're quite a long way away from that. Is my feeling. I mean, there is evidence again in the Arabian Sea. There is evidence, I think, for increasing anoxia, and that's partly driven by warmer water. So obviously, the warmer the water gets, the lower the oxygen saturation. The lower the capacity to hold oxygen gets. So you get lower oxygen concentrations. And there's also some talk about, changes to the monsoon and also changes to the amount of nutrients coming down the system. So that's potentially another hotspot. The North Sea is such a high energy sea. There are times when there's lower oxygen in that sea, but I think on a much larger scale than that, I don't know. I think, if you have systems like the Arabian Sea flipping to anoxic, because at the moment it's suboxic. And what's happening in there is you've got a lot of nitrate buildup. So if that system were to flip anoxic, and there's people doing some work on this at the moment, I think there might be some stories coming out soon. I better not say too much. If that system were to flip anoxic, you might actually see less nitrogen in the ocean because you would have this huge body of currently oxic water that's full of nitrate suddenly being denitrified. But then that's sort of a negative feedback on that. So I think, from my perspective, I think, it is a global issue. There are massive effects on coastlines and ecosystems, but I don't feel. I think the sort of idea of global ocean anoxia is, apart from the sort of case studies I just mentioned, I don't see that happening. It's my feeling.
Great, thank you.
Anybody else have questions? So I have one. So very interesting relationship amongst your watersheds with different loadings, and I'm wondering what will happen if you can reduce the nitrogen loading to the macroalgae vegetation ratio. Will it go right back down the same curve, or is there some sort of hysteresis or something that will make it harder to get back to the way it used to be?
Yeah, I mean, so definitely the paradigm is that it follows very strict hysteresis. It's, I think, if you look at the work of Duarte and people who've sort of thought about this, I think there's even a paper on it, Return to Neverland or something, can you go back down the same curve? And I think the general idea is that you can't once the system's been flipped over. I reckon these systems are actually quite well flushed, to be honest. I do think, within a decade or so you would get a response going back down that curve. I don't know how it would trace the path, but I think you could get that. And yeah, so I mean, Melbourne Water are very interested in that very question. Can we pick an estuary and sort of extend Stringy Creek to that kind of sort of scale?
Right. Good. All right. Thanks.
Picking that estuary is hard. It's very hard. And then undertaking the works to reduce the nutrient loading. So you've got to do the Stringy project, right, which is a decade or two, and then after that's complete, then you can maybe start on the estuary. That's why it's such a
right
down the line.
Yeah, and we've had discussions about that. I mean, you've mentioned the Mississippi River and the Gulf of Mexico, so attempts throughout the whole. Mississippi drains, I think, a third of the United States, so that's a big area to try to control nitrogen inputs over.
Yeah. Yeah, and as Tim said, I mean, Peter Groffman's done lots of work on that.
Yeah. All right, thanks very much. Okay, I think we need to move on. We're, I know, behind schedule, but we'll try to keep going. Our last but not least talk is by Meg Rippy, who's going to talk about FIB removal and biofilters. I can't hear you.
Yeah, you're oops.
I think, did that do it?
Yep, there you go.
Good.
All right. Okay, now I need to find my slides again. Sorry, I'm using Stan's computer, which makes this complicated. Stan, where are my slides on your computer? I have your publication. Mac to PC joys. All right. So, hello everyone. I'm Megan Rippy, and I'm a postdoctoral researcher at the University of California, Irvine. And what I want to talk to you about today is really linking biofilter design to fecal indicator bacteria removal. So we're transitioning from nutrients to fecal indicators. And the real reason I want to talk about fecal indicator bacteria right now in sort of this environmental focused session is because meeting bacteriological water quality criteria has been cited as one of the primary barriers to implementing green infrastructure in urban systems where the end goals are things like human and environmental health. All right, so what exactly are the fecal indicator bacteria? Sort of moving on to slide 2. So fecal indicator bacteria are broadly classified as non-pathogenic enteric bacteria, meaning that they live in the guts of warm-blooded animals. And they tend to have high concentrations in feces, often exceeding 10 to the 7 bacteria per gram of fecal matter. And because they have these high concentrations in feces, they can be used as proxies for inputs of fecal pathogens in drinking and receiving waters. There are 4 major groups of the fecal indicator bacteria: the total coliforms, fecal coliforms, E. coli, and Enterococcus. The total coliforms are a group of gram-negative, rod-shaped bacteria that have both environmental and fecal constituents. The fecal coliforms are a subset of the total coliforms, and then E. coli is a species sort of within the fecal coliforms. The Enterococci are actually, or Enterococcus, are a genus of bacteria that are separate from the coliforms. They are gram-positive coccoid or round-shaped bacteria, and there tend to be about 50 species within that genus. One thing about Enterococcus that you see on slide 3 is that they tend to be the preferred proxy for pathogen inputs in marine receiving waters because they have the highest statistical correlation with human health in those marine waters. Whereas E. coli, sort of on slide 4, are the preferred indicator in freshwater systems. So this means if we were designing a biofilter to meet criteria in freshwater systems, we'd be looking at E. coli. And if we also wanted it to meet criteria in marine systems, we'd have to add on Enterococcus. So a little bit about fecal indicator bacteria in practice, moving on to slide 5. One of the things I want to point out is that they're really imperfect proxies for human pathogens, and that's because they have non-human sources, things like animal feces, for instance, and also there are problems with environmental regrowth of these bacteria, which means that the relationship between the human pathogens and the fecal indicators is not consistent over time. But despite all of these difficulties, these bacteria remain our regulatory currency, reaffirmed as recently as 2012. So they're really relevant from a management perspective still. What exactly are our criteria? In the US, we have a variety of different criteria. We have ones for potable use, sort of drinking water criteria, as well as non-potable use, sort of our recreational water criteria. And for biofilters, probably looking more at the non-potable use criteria. And these come in sort of 2 flavors. You have your sort of statistical criteria, things like geometric mean standards and statistical threshold values, which basically say that a certain percentage of samples must have less than a given concentration of bacteria per month. And then you also have your single sample standards, things like the Beach action value, which just says in a single sample you must have less than a certain concentration of bacteria. So now I'd like to talk a little bit about fecal indicator bacteria in stormwater and dry weather runoff. So we're on slide 6, and compare those concentrations to some of those criteria, the non-potable criteria I was just talking about. And the first point is that fecal indicator bacteria concentrations in stormwater and dry weather runoff are often high. This is nicely illustrated by this table from Greville et al. In 2013, and I should mention that all of the references are in the final slide of this talk if you're interested in any of this in more detail. And they show that the ranges for these fecal indicator bacteria are quite broad. They can get up to about 10 to the 6 bacteria per 100 mil. The medians are also quite high, and if we compare them to the Beach action values in red on the far right, we can see that the median values in stormwater can be 1 to 2 orders of magnitude higher than our water quality criteria. So this really means that sort of moving on to slide 7, that because our modern storm sewers tend to route stormwater away from urban centers and into urban receiving waters to prevent flooding, those receiving waters are often impacted by stormwater-associated contaminants like fecal indicator bacteria. And this is really nicely illustrated by Newport Bay, California. That's that image, the schematic on figure 7, which is actually, if you look at all the blue dots sort of around Newport Bay, blue and red, those are all storm drains. There's actually 219 storm drains that surround Newport Bay, and in a recent publication by myself and colleagues, we illustrate that dry weather discharge from those small storm drains is really a dominant contributor to shoreline fecal indicator bacteria contamination in the bay. So what this means, kind of moving on to slide 8, is that when we think about green infrastructure design, we really need to take fecal indicator bacteria into account. And to kind of hammer this point home, we heard in sort of earlier talk in an earlier session that the cost of redesigning urban water systems to meet water quality criteria and keeping sustainability in mind, things like green infrastructure approaches, is really high, more than $30 billion US just for Southern California. And this means that if we're going to be spending this kind of money, we really want to make sure we're dealing with all of our criteria. So that means including fecal indicator bacteria. So for the remainder of this talk, I want to look at this a little bit from a stormwater biofilter perspective and talk a bit about how we could be able to do that, I guess. So what exactly are stormwater biofilters? We've talked a little bit about this. Stan went over some of it quite nicely. So this is slide 9 now. And really, stormwater biofilters in general are just low-impact development or water-sensitive urban design systems, depending on where you're from, that are intended to remove suites of pollutants from stormwater or wastewater by physical, chemical, or biological means. They tend to be characterized by a small spatial footprint, so taking up about 2.5% of their catchment area, and they have vertical flow through layered media. So what this means is that water comes in sort of in an inflow pipe and enters a ponding zone, like Stan was illustrating. It percolates down vertically through layers of filter media until it enters in a perforated pipe in the bottom of the system. So these are lined in pipe systems I'm talking about. And then it can either flow straight out of the outflow, or in certain system designs, submerged zone systems, you can actually elevate the end of that outflow pipe, creating a saturated or submerged layer at the base of the biofilter that tends to have low oxygen and favor anaerobic microbial processes. Now, in addition to all of this, biofilters are also characterized by their biocomponent, so their vegetation, soil microbes, and animal communities, all of which contribute to the pollutant removal processes as stormwater moves through those biofilters. And sort of as you look at these schematics, it's obvious that there are a lot of different biofilter compartments or components. Your vegetation, you've got the ponding zone, filter media, submerged zone layers, all kinds of things. And so I'm going to argue kind of on slide 10 that if we want to be optimizing biofilters for fecal indicator bacteria removal, we really need to understand both the effects of individual biofilter components on removal and how these components work synergistically to impact removal, because the whole is more than the sum of its parts. But to start, we're going to look at these sort of individual biofilter components effects, and I'm going to talk about it from a very conceptual framework. If you want more details, all of this is presented in more detail in a recent publication of mine in Wires Water. So regarding the filter media compartment, filter media effects on FIB are largely associated with things like straining and physicochemical filtration, and that's because bacteria are really biocolloids. So they're 1 nanometer to 1 micrometer in size, and they're going to be impacted by the processes that affect other colloids. So what is straining? Well, straining is really where colloids become wedged at grain junctions. So in our little cartoon image here, that would be bacterial particle A, or stuck in narrow pore throats. That would be bacterial particle B. And physicochemical filtration is when colloids are colliding with sediment grains, which you can think of as collector particles, so that would be bacterial particle C, or at the air-water interface in sort of an unsaturated system, that would be particle D, and then they're going to attach whenever the attractive forces are exceeding the repulsive forces. And there are a wide range of attractive and repulsive forces that are controlled by the bacteria themselves, by the grain collectors, by the ionic strength of stormwater. It's more than we can get into at this point, but those are just things to keep in mind when thinking about these systems. So moving on to slide 12, we can think about our vegetation compartment. And vegetation could impact fecal indicator bacteria through things like root adsorption and exudate release. So for root adsorption, it's what it sounds like. You're just having your fecal indicator bacteria or your biocolloids directly attaching to roots. That would be particle A. And exudate release occurs because some of these roots are quite leaky. So they can release, in some cases, harmful compounds to bacteria. sort of antimicrobial compounds, but they can also release things like nutrients or other stimulatory compounds, and this is a process called priming. And we don't really know whether or not fecal indicator bacteria are going to be stimulated, so that would be particle B, or inhibited, or a dashed B particle by root exudates, and that's something that people are still looking at. So moving on to our submerged zone compartment on slide 13, submerged zones could impact fecal indicator bacteria removal by a variety of means, things related to competition, biofilm formation, or predation. So looking at competition for a bit, the submerged zone, because it increases saturation, it has the potential to connect microbial communities that would be disconnected in a more unsaturated system, which can increase competition. And it's not totally certain what this will do to fecal indicator bacteria themselves, and that's what's shown in sort of our little particles A here. Some of them are dashed, indicating they're dying, and some of them have solid boundary, indicating that they're doing just fine. And it's likely to depend on the communities that are interacting, that are competing. Similarly, when we look at biofilm formation, it's possible that the increased moisture in submerged zone systems could lead to more extensive or expansive biofilm growth. And this could increase fecal indicator bacteria capture, but the effects on survival are less well known, and once again are likely to be linked to the actual constituents of that biofilm. So those are shown in particles B and sort of dashed particle B. And then the final one, sort of related to predation, we know that moisture can increase the mobility and the abundance of protozoa in soil systems, which could increase grazing pressure. So that's sort of our little green particle C, which look like they've been swallowed by little gray hedgehogs. Those are my illustrations of protozoa. Not very artistically talented in that regard. But we also know that at some point, it's going to be too moist even for the soil protozoa. So that's going to have a limit at some point. The final thing I want to point out here, sort of moving on to slide 14, is that all three of these biofilter components can impact hydraulic residence time distributions. So I've shown an actual biofilter residence time distribution from a Parker et al. Submitted manuscript, so it's not published yet. And you've got residence time in minutes on the x-axis and salt concentration, a conservative tracer concentration, on the y-axis. And I've got little arrows linking each of the different biofilter compartments to the residence time distribution. So for our vegetated compartment, you could imagine that roots are going to promote macropore formation. And what that means is that you can have roots that grow down into the biofilter, then maybe they die back a little bit, forming a preferential flow path in that system that could result in having lower residence times in your system. On the sort of filter media side of things, your grain size distribution matters. You could have a high percentage of fines, for instance, in your system, and that could increase the residence time in the system if, as the water is moving sort of through those fines, you get more friction, for instance. And if you go look at the submerged zone, well, one of these things that the submerged zone does is it creates sort of a enhanced moisture in those dry periods between storms. So you get reduced fissure formation and less cracking, so fewer preferential flow paths, which could, increase the residence time in the system. Similarly, biofilm formation, which we just talked about, could also increase the residence time in the system. So really the take-home here is that the effects of individual biofilter components on fecal indicator bacteria removal can be direct, which is what we were talking about in sort of the three previous slides, or indirect through changes to hydraulic residence time distributions. So moving on to slide 15, this means that we can sort of create a simple conceptual model for fecal indicator bacteria removal by biofilters, where just we say that multiple different biofilter design components have the capacity to impact fecal indicator bacteria removal, things like filter media, vegetation, and submerged zones, and acknowledge that the effects of these components may be direct or indirect through changing hydraulic residence time. So what I'd like to ask now, sort of on slide 16, is whether or not there are any specific components of biofilters or sets of components that are logical engineering design targets for improved fecal indicator bacteria removal. And I'm going to argue that in order to address this question, we need to evaluate the effects of biofilter design on fecal indicator bacteria removal holistically, looking across all components to avoid masking or misattributing effects. So how are we going to do this? Well, I think the first step is to compile primary literature on fecal indicator bacteria removal by biofilters, performing a kind of meta-analysis. and then using that data, perform some kind of path analysis using something like structural equation models in order to identify optimal networks of design elements that favor fecal indicator bacteria removal. And I'll talk a little bit more about structural equation models in a bit, but regarding the primary literature, sort of the meta-analysis, some of the key pieces of information that we want to make sure we have are things like log 10 fecal indicator bacteria removal values, vegetation presence and type, things like grasses, sedges, shrubs at a very simple level, filter media percent fines, submerged zone presence absence, and infiltration rate, which I'm using as a mediocre proxy for flow effects, because we don't often have information about the hydraulic residence time in these systems, and so sometimes the best we can do is infiltration rate. So now I'd like to talk a little bit about the meta-analysis that we performed. This is on slide 18, and this is unpublished information, so I can't give you a citation for it. But basically what we did is we did a web of knowledge and Google Scholar search looking for the terms biofilter, bioinfiltration, biofiltration, bioretention, or rain garden, and then fecal indicator bacteria, E. coli, Enterococcus, or coliform. And this found about 107 publications. And then we read the abstracts of all of these different publications, and to determine whether or not they were relevant, if they provided information on all the different metrics we wanted, and to make sure that they weren't duplicate studies reporting on the same data. And that left us with a surprisingly small number of studies. It's about 13 biofilter studies from across the globe, though it covered about 350 different biofilter runs, so there's a lot of data nested within those studies, luckily. 5 of these were from Australia, 7 from the United States, including Texas, North Carolina, and Maryland, and 1 from Israel. Regarding sort of the spatial scope of these studies, 5 of them were evaluating small biofilter mesocosms in a greenhouse or a lab, and 8 were looking at more permanent outdoor biofilters or large field mesocosms. And it's important to point out that the biofilter design varied widely across studies, because of course in order to look at the effects of different sort of design arrangements, we need to have that variability. Regarding plants, there were between 0 and 12 species planted in these systems, including grasses, sedges, and shrubs. Filter media composition ranged from between 3 and 46% fine sediment, and the drainage configurations could either have submerged zones present or absent. So once we have sort of our data from our meta-analysis, the next step on slide 19 is to perform a path analysis using structural equation models. So structural equation models are really just a statistical modeling method for evaluating networks of relationships amongst model components, in this case our biofilter design elements, where we use maximum likelihood statistics to estimate relationship strength. So I'm showing on the right sort of a schematic of our structural equation model of our biofilter, where we have our different biofilter design elements. So we have plant type, grasses, sedges, and shrubs. Filter media is indicated as filter media percent fines, and then we have submerged zone presence absence, all of which can impact log 10 fecal indicator bacteria removal. And one of the really great things about structural equation models that differentiates them from things like multiple linear regression is that you can evaluate both direct and indirect pathways. So here we also have infiltration rate in our model, and all of our different elements can either impact FIB removal directly or indirectly through changing infiltration rate. And on the left here, I have a couple of arrows, and I'm just pointing this out because it's going to be carried through for the rest of these structural equation model slides. When I'm talking about significant effects, they're going to be indicated with colored arrows, green for positive, red for negative, and big and bold for strong effects. And I'll also, to indicate sort of the significance of those effects, often give you standardized coefficients, and those are reported on a 0 to 1 scale, where 1 is the strongest it can be, and 0 is no relationship. All right. So moving on to slide 20, when we perform this structural equation models analysis, what biofilter design elements do we find contribute most significantly to fecal indicator bacteria removal? Well, I think the key point I need to make is that plant type, fines, and submerged zones all impact fecal indicator bacteria removal. However, submerged zone presence matters the most, and that's both direct and positive effects on fecal indicator bacteria removal and indirect positive effects where the submerged zone is decreasing infiltration rate and therefore increasing fecal indicator bacteria removal. Regarding filter media percent fines, we see only a direct effect, and it's positive on fecal indicator bacteria removal, whereas in contrast, the shrubs and grasses, sort of two of our plant types, are only impacting removal indirectly through changing infiltration rate. And interestingly, the effect of shrubs is to decrease infiltration rate, therefore increasing fecal indicator bacteria removal, whereas grasses are actually doing the opposite. They're increasing infiltration rate and therefore decreasing fecal indicator bacteria removal. An important thing I need to point out is that the model is only explaining about 32% of our total variance. This could be because, I mean, at heart, these are biological systems, so there's a lot of variability underlying these linkages. However, it's also possible and likely that we're missing model components. And a really likely one, of course, is climate. So if we move on to slide 21, I want to point out that climate matters. Indeed, if we include antecedent dry period, so that period between storms, the length of that period, as a moderating variable in our structural equation model, which basically allows the model to take on different configurations when the antecedent dry period is less than 10 days, so a wet climate or wet season, versus when it is greater than or equal to 10 days, so a drier climate or a dry season. And if you look at sort of our wet climate, wet season model, we see that fecal indicator bacteria removal is impacted most by the infiltration rate. So any reduction in the infiltration rate is going to increase fecal indicator bacteria removal. Whereas if we move into drier climates, we see that the submerged zone presence-absence is what matters most, and the presence has a positive impact on fecal indicator bacteria removal. Infiltration rate matters much less in that case. So the take-home message of all of this for me, and I'm going to give you a couple of these, this is sort of the first one, is that submerged zones, vegetation type, and percent fines, and infiltration rate are all important design elements impacting fecal indicator bacteria removal. However, submerged zones and infiltration rate matter the most. Submerged zones in dry climates and infiltration rate in wet climates. Then you've got plant selection, particularly shrubs, which were consistently decreasing infiltration rate, thereby increasing fecal indicator bacteria removal. And then filter media percent fines, which had by and large, sort of across all our models, a consistent positive effect on fecal indicator bacteria removal. And sort of looking at slide 22, if we want to sort of move away from models and take a sort of peek at the data itself, and we categorize it relative to those processes that were deemed most important. So we have submerged zone presence-absence on the x-axis, the log of the infiltration rate on the y-axis, and the log of the antecedent dry period, that sort of climate variable on the z-axis, our vertical axis. And the other thing I need to point out is that the color of each of these points is the log 10 FIB removal value. So we're going from a very high removal, greater than 3 log reduction in the red, to actual leaching out of the system, the blue colors on the bottom. And it's clear when you look at this that the highest bacteria removals, sort of where I've circled in the red oval, are systems that have submerged zones. They have moderate to low infiltration rates, and they have actually a long antecedent dry period, interestingly enough. Whereas if you want those systems that are doing poorly for fecal indicator bacteria removal, and of course we don't want them, but those are those systems that don't have a submerged zone. They have really high infiltration rates, and they also have that long antecedent dry period. Of course, this is not a perfect relationship. There are outliers. In fact, I've circled one of the ones there in blue just to show that there are exceptions to the rule. Another thing that I want to point out here, because I think it's really important, sort of moving on to slide 23, is while it might be really tempting to sort of look at this data and say, okay, we want systems that have really low infiltration rate, because that's going to really boost our fecal indicator bacteria removal, we need to keep other biofilter functions in mind when we're optimizing for fecal indicator bacteria removal to ensure that the trade-offs that we wind up with are acceptable. Because if we push that infiltration rate to really low infiltration rates, really what's going to happen in practice is that we're going to have a lot of water overflowing and going into the storm drain. We have poor volume control. So essentially we're just not treating that water, which is actually worse than the other alternative. So these are things we need to think about carefully. So take-home message 2, sort of moving on to slide 24, is that although we have successfully identified some key biofilter components that are logical engineering design targets for improved bacterial removal, uncertainties regarding why and how those features improve removal still remain. And to sort of illustrate this, I put the kind of biofilter model we were just playing with on the top, and behind that we have all of this complexity, and it's really a simplified version of the possible complexity space that we could be dealing with, looking at things like filter media amendments, protozoan grazing, soil microbiome, root architecture, root exudates, and all this, that, and the other. And I would argue that we need to understand the mechanisms that underlie the performance of individual biofilter components in order to further advance biofilter design. And currently there are some really great studies that are looking at characterizing some of this complexity, looking at filter media amendments, the soil microbiome, and invertebrate macrofauna in particular. But I feel that we need to remember, sort of as we're continuing to move into these more, I guess, novel spaces, that we also, as we're reporting sort of our novel findings, need to also report some of the traditional things that we were originally reporting, so that we can still keep looking at the system as a whole, sort of evaluating how all these compartment effects affect each other. And that way we don't wind up with some extremely good but disconnected studies in each of these areas that we can't consolidate into a holistic evaluation of biofilter performance and the things that we really need to target to improve our our removal capacity and the effectiveness of these systems in the urban environment. So with that, I'm going to conclude my talk. At the back here I have a set of references, just a really brief set actually, that talk a little bit more about fecal indicator bacteria in stormwater, the environment, and more broadly fecal indicator bacteria removal mechanisms by biofilters. If you're interested in diving into this further, that's sort of slide 26. And then the final two slides of the talk are actually just in case anybody wants to do more than a conceptual view of sort of the effects of those individual design components on FIB removal. These look at things a little bit more quantitatively, going through sort of a probability distribution and bootstrapped approach to show which individual components have significant effects, and they actually give the actual log reduction values. So if you're interested in that, you can look at slides 27 and 28. So at that point, I think I'm done, and thanks very much. I'm happy to take any questions.
Okay, thanks very much, Beck. Yeah, any questions?
Yeah, that was a very nice talk. What are your thoughts then on, so my take-home message from this as well is that you think allelopathy from plants is probably not a major role based on your analysis, is that right? And it's the effect of plants, from what I understand you said, is basically driven through its effect on infiltration rate. So it's really physical effects rather than biological effects.
I would say that that's in part a limitation of the kind of analysis I was able to do. I don't know that anybody has really well characterized the effects of plants on fecal indicator bacteria in these systems. I know Anna Delitic and her group are going to be doing more work in that direction, but because the kinds of data that I could collect for a meta-analysis that are common across all those studies are more focused on flow effects, that may be part of why we see those as emerging. So I wouldn't necessarily rule them out, but I think it's an area that's important to look at more.
No, but a priori I'm a bit skeptical of that.
And they may or may not, I don't know.
I can see the attraction of the idea, but I'm not convinced. But anyway, yeah, I thought that was interesting. Yeah. And also, just one final comment. I really liked, it's not directly related to the material, but I did like your point about undertaking studies which are sort of parsimonious to one another, or not parsimonious, probably complementary to one another, rather than, this is one of the things with science, is it drives you to everyone to do something extremely novel, and at the same time, it sort of means that, in a way, you're not quite pulling in the same direction. So it doesn't lend itself well to this sort of the nice meta-analyses. But then when you go to publish a study which doesn't have that extremely novel hook, then you'll get smashed. but it could actually be very important because it's providing a very important piece of the bigger picture puzzle. I think that's a good conundrum about the current system that we operate under.
Yeah, thank you. Any other questions from anybody?
So I have to ask a question about the plants, of course.
Sure, yeah, please do.
It's kind of surprising, not whether they did or didn't have an effect, but sort of the three different types that you found. So at least in your structure equation model, no effects from sedges. Whereas when, for the other sorts of removals, sedges are usually, an effective plant type.
Yeah, that's been an interesting sort of conundrum when people have been doing these studies and they look at the performance of Carex in particular. Carex does not seem to improve removal of fecal indicator bacteria, but it's great for nitrogen, great for phosphorus. So, yeah, I don't necessarily know fully why that is, but that does seem to be true. Though there, in the wet system model, there was a direct effect of sedges on removal, and a negative effect actually. So they weren't helping. But so they can do something, but it's really unclear at this point exactly what they're doing.
Yeah, I mean, I like the way you went through the possible mechanisms. And I think the problem is we don't actually understand what the plants are doing. So we don't know what they're doing for the nutrients or for the metals or anything, and so we don't really understand what they'd be doing for the bacteria for the most part. Although you talked about, like, for roots, I mean, if they're big roots, they can, we definitely understand some sort of changes in physical, but not very much about the other ways they could be acting.
And I wouldn't be at all surprised if many of their effects are through the microbiome, sort of the native soil microbiome, and effects and interactions between fecal indicator bacteria and that microbiome.
Right.
And I know that there's a big sort of microbiome project that is currently being started at Monash. So hopefully they'll provide some insight in that regard.
Yeah, okay, that could be useful.
I'll put on my engineering hat too and say that the other wrinkle here may be a timescale effect. So typically we would measure removal over a shorter timescale. We went to Monash and ran some biofilter experiments in which we added sewage and looked at the removal rate. And so there's an initial removal that occurs that we're measuring, and that could be more physically based. Right, and we in fact find that the plants actually reduce that physically based removal because they create fast-moving water, the sedges anyway, which essentially reduce the residence time of the water in the biofilter.
Right.
On the other hand, you have a longer time scale, which we may not be measuring, which is what happens to those attached bacteria over time, which has to do with really the microbial community that's present and its interaction with the plants. And so the plants could have a really adverse effect on fecal indicator bacteria over those longer time scales by promoting a diverse community of organisms that are consuming them, for example, whereas over a shorter time scale could actually, the plants could reduce filtration, for example.
And that's one of the arguments for the submerged zone effect in the long term, is that you're essentially holding more of the water than you would have otherwise in the system, and that includes the fecal indicator bacteria associated with that, so more time to die, essentially.
Although, you also talked about regrowth possibilities, and at least in marine, the Enterococcus is potential, especially for regrowth. Did you pay any? So you're lumping all FIB together here. Did you look at? Or
I did parse them out. The problem being that I wouldn't trust at this point the data for Enterococci because most people have been focusing on E. coli, given that it's more of a freshwater emphasis.
Right.
So it's kind of unclear to me at this point whether Enterococci are removed more or less by these systems and how it all shakes out.
Yeah. Okay. Interesting. Any other questions? Okay. Well, thank you. So we're supposed to go to a roundtable now. We're pretty significantly over our time. So I guess it depends on whether anybody wants to stay and have questions for the group, or whether we want to call it a day. So anybody who hasn't had a chance to speak, who wants to ask any questions?
I would particularly call out Trish if she's on. I see that her window's there, but I don't know if she's actually available to talk. Trish Holden. And no response.
Yeah, she may be away.
Okay. What about Ashmita and Andrew and Brandon?
I have one final question. Perran, at the end of your talk, you brought up that we need to look at agricultural areas a bit, with LID for treating nutrients. And I was wondering, what type of LID do you think you would use in agricultural areas? Because I was thinking, you have so many different types of pollution there, and would biofilters work in a situation like that, or would you use wetlands, or do you think there's something else that you would lean toward?
Well, my understanding is that in the example, returning to the example of the Mississippi, they're using wetlands, the traditional wetlands. So I think, yeah, I would imagine that's probably how you would do it.
Yeah.
In Australia, I suspect it might be, well, I guess it's not LID then so much, but I think it's all going to come back down to water conservation efforts. If you're conserving water, you're effectively conserving runoff then. So in dry climate like Australia's, where we're on the edge of agriculture, I suspect in a way that a lot of that is going to be driven by cold hard efficiency and money rather than any environmental regulation. Right. Although I suspect it'll be a combination of both. But in terms of the method, yeah, I would have thought, any remaining material that comes off, it would have to be the traditional wetlands, really.
Yeah, it seems
Although, the effectiveness of them, biofilters, I just think are much more effective and reliable. It comes down to clogging, I suppose.
That's what I was wondering about, because you have all that soil moving off the landscape, all that erosion, and you also have massive amounts of water.
So one of the things that they try to have these riparian strips. So it depends on whether you're getting runoff into the streams over the land or not. So in the cases where they have that, they'll try to have basically it's like a bioswale, but it's just a strip that intercepts the water and particles. And that we talk about co-benefits, right? There's a lot of other benefits that come from that, but it's one of the sort of a transition that they try to design.
Right, like a buffer, like just a riparian buffer.
Exactly, just like a riparian buffer. And I actually don't know if they do anything unique about that instead of just planting a riparian buffer, but by putting that between the fields and the water body, then it can remove the nutrients. But when you talk about the Mississippi, you're talking about a lot of acres.
Yeah, you need a big buffer.
It's a pretty, whether it's wetlands or whether it's a buffer like that, it's a pretty substantial investment to try to do that.
I think the key is really to do it right up in the top of the stream where you've got a large surface area of bank to paddock, basically. Right up in the small headwaters, I think, is the key. Yeah. And that's not the most obvious place.
No, because it's up in Ohio, right? And so it's pretty hard to convince the farmers up in some high in the tributaries in Ohio that they need to reduce their nitrogen runoff to avoid the dead zone in the Gulf of Mexico. So it's just it's 1,000 miles away. It's just a hard sell, I think.
Yeah.
So.
Thanks.
Other questions?
Yeah, I had one sort of general question / thought. We've heard a lot of different talks, not just in this session, but over the last couple of sessions, looking at biofilters and LID in general as tools for treating water, but thinking about different endpoints, fecal indicator bacteria or nitrate, micropollutants, pharmaceuticals, you name it. There's a wide range of things we might be worried about. I guess just from your perspective, Rich, and then maybe more generally, kind of what is the most important thing to be focused on? I mean, what have we already figured out versus what is still a really huge and important open question? And kind of by way of bringing in the talks we've heard specifically today, I'm also thinking about Emily Payne's the figure from Emily Payne's paper that Perran showed, that showed that basically assimilation was kind of the major answer for nitrate removal by plants. So, I mean, some of these mechanisms, maybe we've checked the box and we're done, whereas other things we really don't know very much. And I'm just kind of curious to get your assessment of kind of where we're at in that spectrum.
Wow. Okay. Well, nice, easy question, Stan. Thanks.
I don't have to answer it.
Yeah. So, I mean, I think it's hard because it's so different in so many different places, and it depends on what you do with the water. So you gave a really nice, you laid out the different ways that we can use biofilters in terms of, emphasizing infiltration or capture, and then you also mentioned concerns about what's going to happen to those contaminants as they move through a biofilter into wherever they're going to go, especially into groundwater. And so, here in California, mostly it seems like we're not capturing water right now. So that's really interesting. And you're talking about, the ratio from infiltration to harvesting. Well, we're not harvesting. Yeah, it's virtually zero.
Yeah.
So I think that what's the most important or critical factor depends on whether you're harvesting or not, a lot, because right now I don't think, I mean, this is not right, so I think we need to know it more, but right now we're not that concerned about what happens to the pollutants in the water when it's just getting infiltrated, because we're concerned about capturing the water and keeping it from moving into the streams. And so as far as we're concerned, mostly we think that we've solved the pollution problem just by keeping it in the biofilter. But in the long term, I don't think that's really correct. So we need to be paying a lot more attention. I mean, what Meg was talking about, everyone's talking about these pollutants, and we're starting to try to understand what happens to them so we can design the biofilters better for those things. But I mean, I have to say right now in Southern California, we're not. So we don't have the science, but we also, I don't think in the planning and policy arena, I don't think we're really even asking the right questions or framing the issue correctly yet. I mean, that's even just on the collection side. But on the harvesting side, which is I think where we really should be moving to, I mean, I'll turn that question back to you. Why aren't we talking about harvesting?
Mm-hmm.
I mean, in Australia, they do some at least.
Right. So I asked this question to Scott Taylor in the presentation day before yesterday, and because when he was giving his talk, and I've heard this over and over again, folks who are sort of deeply enmeshed in the LID issue in Southern California absolutely equate LID to infiltration. Those are absolutely synonymous. And so, you'll ask, why don't you have more LID in Southern California? The answer will be, well, we've got groundwater contamination, we have clay, it's not infiltrative, so forth and so on. And so I asked him this. I said, I'm really frustrated because there's just this, it's like completely off the radar, And he said, yeah, no, it's true that we don't talk about it. It's because of storage. So we don't have adequate storage because we get so much of our rain in a very short period of time. And the land cost is so high that there's just not sufficient storage. And I think a lot of people like Scott would say, even on a distributed basis, there isn't enough storage to really make a big difference. So you have to do something really dramatic with storage. And then probably you're talking about more centralized facilities in one form or another. So that may be what sort of shapes, it may be a climate issue that shapes the dialogue and even the understanding of what LID is in Southern California compared to Melbourne, where you have, Perran can tell you, 4 seasons in a day, right?
Yeah. Yeah.
So their harvesting can be, you can set it up so that that you're likely to have enough on-site storage to both create reliability in your supply, say for toilet flushing, as well as reduce formal drainage to streams.
I mean, that makes some sense, but I think that is not really, doesn't have to be a driver, because I mean, it's true, we don't do much storage, right? It's very hard. We're not putting cisterns in, hardly ever, but we could. And I think that capturing, so I mean, I've got rain barrels, right? But they're pretty useless. right? I mean, they completely fill up with an 1/8 inch of rain, and then they're full when it's raining. Right? And
Right.
so, I mean, that's an exaggeration because we do have dry spells in the wintertime, and we do use it. But the storage for irrigation anyway is not very useful. But we're still flushing toilets, and we're doing these other things, and we could. I think the storage capacity that you could have on a site level could take a big part of the potable water use away.
I think maybe this is all a building code issue.
Yeah.
You know, if you change building codes, I think as they've done in Australia, so that you're required to include storage as you build new homes or redevelop areas, that would have a big impact in the long run. And the other thing that Scott said, which I think is probably true, is that the pricing is terrible. So he calculated how much money he saved by installing all of his rain barrels, and it worked out to, I think it was 2 cents.
10 cents, I think.
Yeah. Well, no, that's how much money he would save, but then of course it costs him quite a bit of money to put in these systems, and so so it's just economically the incentive is not there because the water is so subsidized, and that's account for externalities. So
and that also, I mean, when you're moving away from rain gardens up to larger scales, to regional infiltration basins and things like that, the costing I see on that also drives them to these larger centralized capture systems, just because the cost per acre foot or whatever is so much less. So I don't know. But that didn't answer the science parts. I mean, I think there's still a lot of science that we need to know, but it does seem like it's actually policy, governance, economics, maybe that is our biggest impediment right now.
Well, and on the science side, I mean, I think the ecology is a big factor, right? I mean, coming up with systems which are resilient, that don't require, irrigation during dry weather periods, maybe something hybrid like what Anna was talking about with, using gray water during dry weather periods and rainwater other times. But also then just confronting issues of, do you want these systems, what other co-benefits do you want these systems to have? Do you want them to be, biodiversity islands? In that case, do you want invasives and ornamentals, or do you want native plants? And how is, are you going to get public acceptance of that? I mean, I think those are really critical issues as well. Great science out there too, but after Perran's talk, I mean, nitrate, we can't remove nitrate anyway, so.
Well, I was just going to add that, with having an issue of storage, I mean, we're much of our attention on stormwater, which in Southern California doesn't necessarily make a lot of sense as far as a resource. When we haven't spent nearly as much time on gray water. And when you have a constant supply of something like gray water, does storage become less of an issue? Because you don't need to collect everything you can and store it up these long periods of time. I mean, you're getting a daily supply.
Right.
Yeah. Sorry, go ahead.
Oh, no, after you.
Yeah, no, I was just going to say I think that that's absolutely right, that that again it becomes a building code issue. So the plumbing codes have to be in place to allow that, which I don't think they are right now in Southern California. And then you have to have the systems and sort of public acceptance in place. But yeah, definitely. The other would be dry weather runoff. Because we import all that water, it ends up as urban slobber, which could absolutely be captured and used and reduce, not only create a new water supply, but reduce water quality impacts downstream. So.
The other thing that I was thinking about is that a lot of these systems that we're talking about putting in are biological systems, and they have a certain amount of inherent high variability in terms of their performance. So it's going to be trying to figure out how we move from systems that we've trusted their performance, that what they do is they deliver a consistent performance always, to systems that are more distributed but highly variable. They're greener, they're sustainable, but there's this trade-off here. And how we balance that when we sort of move forward to protect both the environment and people, because we don't want to have an instance where everything fails all at once. So that's part of the challenge too, is a sort of as a sort of ecologist training, I'm very comfortable with that uncertainty. I'm like, oh yeah, 32% of the variance, great. But that's not going to work.
You're talking to a public health official.
Yeah, it's like, well, 32% of the time we know what's going to happen. Yeah.
Any other thoughts? Any other comments?
Ashmita and Brandon, do you are you still there? Your pictures are.
Yeah, I'm here. I don't have any more comments to add to what's been said, but great talks. Yeah, thanks.
Great, Ashmita. I think she's present in picture only.
She was here. I saw her live for a while back.
Yeah, no worries.
Yeah.
All right.
Okay, well, that's excellent. Thanks everyone for great talks and good discussion. And
yeah, thanks for chairing it, Rich, and thanks for getting it organised, Stan and James. It's very good.
Thank you.
Yeah, thank you for the great talks. It was a lot of fun, actually.
Yeah, that's a good way of doing things, actually.
Yeah.
So James comes on. That means that our time is over. So he usually closes down. So.
Yeah, and just to all those who are still watching, there is a survey that we're requesting that you take if you've been present for the symposia. So that's actually located on the event page along with the YouTube page. So if you could take that if you have a moment, that would be great. And thank you for watching.
All right. See you guys.
Thanks.